Hello. So is my screen visible?
Yes, sir.
Yeah. So we almost end of this particular course. Hopefully some of you have been even actually most of you have been attempted that OPP examination also. Maybe some technical issue was done in the first session. Maybe other session was done well. Am I right? Any other
Yeah.
issues? Okay. So today we are here for end term revision session exclusive. This session is on week 9 and 11. So if you want to see that any revisions of that previous quiz 1, quiz 2, which is quick overview, that overview help you that how to solve a problem which belongs to a particular week. Similar lines we are going that week 9 and 10 also, but week 9 and 10, so the concept we are trying to use it while you are solving a problem. So basically, first part we are concentrating on that week number 9. So the week number 9 is completely on DP, dynamic programming. This is a one algorithm strategy, like we have divide and conquer, greedy method. Similar way, dynamic programming is one method of algorithms, like one approach, one strategy of algorithms. So when we are going for dynamic programming strategy, the common problems are there. Common, this is some standard. Yeah, somebody wants to ask something. Hello.
Sir, I think someone asked when will the mock anthem release?
That is, I think today is Wednesday. Tomorrow they'll release. Friday we have a revision session on that.
Okay. Okay, sir.
Tomorrow,
Okay.
because Friday, Sunday is your end term. So that Friday session, we want to have a revision session on the mock, so that tomorrow we'll release. Okay. Okay. Yeah. So there are standard algorithms in the dynamic programming. If you see that standard algorithms, the first basic one is the grid path. Say first we'll finish up that week 9, then we'll think about the week 11. So these are some standard algorithms are there, like grid path algorithm. So where you have a grid, so moving from one source horizon to a target, like column and row and column is there. How many ways to reach that from a source to destination? From a source means maybe 0 0, we are trying to reach that 3 4, like is third row and fourth column, something like that. So that is one particular standard problem. And another problem, so we have already discussed, of course, while you're solving the problem also we'll get it, like so longest common subword. So this is another one, longest common subword, common subword. So in short form we can say that LCW. So like two strings are there, we are trying to compare the two strings where they are matching, which characters they are matching, that particular common subsequence we are trying to find out, common subsequence word. And similar way, there is one more is edit distance sequence, what you call edit distance. So like one particular string we want to convert into other string. While we are converting one string to another string, how many edit operations we need to do? So these are some kind of standard algorithms in the dynamic programming. So generally we ask these questions only on the basis of these particular standard algorithms. If you could see that summary of ninth week, you will understand. But anyway, while we are solving the problems, we'll understand. So let me jump that some standard questions which we are getting from week
Sir,
9. Hello.
sir, from week 9, there is one topic also, matrix
Yeah,
multiplication.
that's what thing. Lot of thing is there. While we are solving the question, we'll understand the particular how
Okay.
to how to solve that one itself. You'll understand what concept behind it. Okay. Yeah.
Okay, got it.
So these are some standard questions. See, look at here. So there is a code snippet is given. Consider the program is finding that nth Fibonacci number. Which of the following approach is being used? Like what approach is used? First, let us understand before we are seeing the options. So in the dynamic programming, basically there are two approaches are there. So one is that memoization, and the next one is bottom up approach. What do you call, bottom up approach. So first let us you understand the dynamic approach is, before the dynamic approach we have already recursion. Of course the recursion we use it in the dynamic programming, but a clever recursion we'll write it. So dynamic programming, we can say that it's a clever recursion. What you call, in a clever way we try to use it. Or why would you say that clever is, if in the case of recursion there might be a overlapping of function you are calling, like already called function you are trying to call another time, so that it's wasting of CPU cycles. Like, you're trying to execute one more time. Already we have a solution, but we are trying to execute it. To avoid it, we try to go for that, the memoization. What do you call, already executed results, we want to put it into one particular place. That I want to utilize it. Again, I don't want to call that recursion. So that what we call, clever recursion. But in the case of bottom-up approach, what you call is, we are taking a base solution, that base solution we are using to compute that current solution. Current solution is calculated from the previous solution, like, so once it is calculated, this current solution, it will be helpful for that next solution. So there is one excellent diagram was given in the summary document. Even I'll show that. Now let us see this particular approach. Whatever, this particular problem, there is a dictionary is used. Am I right? Is it dictionary? Yeah, cool. So now the Fibonacci function they are calling, if the base case is below 1 or equal to 1, simply we are storing t of n equal to n. So it's a dictionary, means what happens, it is going to store that n with n value. So whenever 0 or 1 is there, 0th dictionary key will store 0, 1 dictionary will store 1. Is it right? Is it right? Fine. So now this next time, whenever, like, n value more than 1 is there, more than 1 means this if condition is not satisfied, this if condition is executed. So if n is not in the t, that means it is not available, means we are trying to call the previous two, values, like current Fibonacci we are getting with some of the previous two Fibonacci's. Am I right? Current Fibonacci you are getting some of the previous two Fibonacci's. Once we got the new Fibonacci, what it will do is, immediately it will do that, it will store it here. So 0th Fibonacci, first Fibonacci, second Fibonacci, again it will store 1. Is it right? Third Fibonacci will store 2. Fourth Fibonacci will store this, 2 and 1. So that fourth Fibonacci is 3. Fifth Fibonacci is 5. Am I right? Sixth Fibonacci is 8. Is it right?
Yes, sir.
So what is the use of this one is, whenever you are calculating fifth Fibonacci, already available third Fibonacci and fourth Fibonacci is used. Is it right?
Yeah.
Is it right? So
Yes.
that's the thing. Whenever this particular n is a new n, we are calculating. If n is already calculated and available, what we do is return that whatever the value already exists. So this method is called either memoization or bottom-up approach. What is this?
Memoization.
Yes. So please look at that options. Is it a simple recursion? Definitely no, because simple recursion doesn't store the results in any memory space. We don't use any dictionary or something. Just you do that recursive call, so that there is a overlapping is happening. So dynamic programming, actually this option they have to give it. Memoization also dynamic programming only. This is bottom-up approach. So bottom-up approach, they're supposed to give it bottom-up approach. Of course, it is missing maybe. The right option is this. If you would like to see the bottom-up approach, what is this? You can see that there is a GitHub summary. Is my screen visible?
Yes, sir.
So let's go for directly the summary of the 9th week. Yes, there is a dynamic programming. Here it is. Please look at here. So initially they are trying to have this, 0th one and first one values. We want to store it. To compute that second Fibonacci, we try to take the previous two Fibonacci's, like first Fibonacci and 0th Fibonacci. To compute the third Fibonacci, we try to use the first Fibonacci and second Fibonacci, we try to add it. To compute the third Fibonacci, we are trying to use it 1 and 2. To compute fourth Fibonacci, we try to use 2 and 3. So in this way, we want to do that. So please look at here. You can see this. This is a function. In this, initially they stored all of the values with zeros. Is it right? Is it right?
Yeah.
So a list is created. The list, it contains the number of elements plus 1. For example, if you call it is fifth Fibonacci you wanted, there is 6 cells are created, 6 list of elements are created. All of them contain 0 because n plus 1 they created, no? Then initially they stored 0th one, always it contains 0, but first value they stored it is 1. So that what happens, 0th one and first one is helping to compute that the second Fibonacci. First one and second one is helping to compute the third Fibonacci. The strategy they are applying, see, look at here. They are repeating from the second Fibonacci. Already 0th Fibonacci is there. First Fibonacci is there. We are trying to compute the second Fibonacci onwards. So to compute the second Fibonacci, we are trying to do that. Current I value is 2. 2 minus 2, 0. Plus 2 minus 1, 1. So 0th Fibonacci plus first Fibonacci, we are computing the second Fibonacci. Similar with third Fibonacci is second Fibonacci plus first Fibonacci. So in this way, it is computed. This completely it is computed. So once it is computed, final result is available in the last index position. Is it right? The last
Yes,
index
sir.
position only, that is. So it is called, bottom-up approach. Already base values will fix it. From the base value, we want to compute the current value. So once already just you can go for, I said about, grid path, LCW, longest common subsequence, edit distance, all of them will use it strict dynamic programming, that too bottom-up approach only. We are trying to use bottom-up approach. Already we take a base values. From the base, we are trying to, climbing that towards the top of the solution. From the sub problems to main problem, we are traversing. So we are computing. So this is, this is what the particular question. So did you understand?
Yes, sir.
Fine. So now this is one, standard problem in the dynamic programming. Remember, when we are asking in the quiz examination, because n term is not programming based, so you have that MCQ or MSQ or numerical type, So when we are trying to ask you that grid path or thing, at most we give it like 4x4 matrix or 4x3. So at most we go up to that 5x5 only, like we want to make to compute a grid path. So let's look at what is grid path is. See, we are trying to move or traverse, we are trying to travel from 0 to 4 5. What are the different unique ways to reach this 0 to 4 5? Different unique ways. Different unique ways means either you can go so 0 to 4 5 in this way. So either you can go in this way. So like that, how many different ways are there? But remember, there is a condition was given. The traveling can be done at one step right or one step up, so that we can move one step right or one step up. There is no chance of moving left. There is no chance of moving down. So always we are trying to move that. So one step towards right side, one step towards, top. So now one more thing they are talking about. The gray box, the gray box is there. See, look at, they are telling that one gray box is fixed. That is, this location. That represents blockage. Blockage means we cannot travel in that way. You cannot move in that way. That way is completely blocked. Did you understand?
Yes, sir.
So please remember, this particular grid paths we are representing in this way, like these dots. This is what the dots. So that locations we are calling it is valid grid points. Now let us see that how to solve that. What are the different bases? So whenever we want to move it, so basic fundamentally we are going how to it is from 0 to 0 1 we want to move. It means how many steps you are going? 0 to 0 1.
One.
So 1. Similar way, we are trying to go that 0 to 0 2. We are going how many steps? 2. Is it right? Hello.
Yeah, we are
Yes,
going
sir.
to.
So we are going one step forward, one step forward. So to go to this point, we need one more step. To go to this point, we need one more step. Is it right? Is
Yes,
it right?
sir.
Yes, sir.
This is a standard one. What we call this standard one is called base case. First, we fill the base case. Similar way, we want to go in this way, 0 to 1 0, because we are incrementing rows. This is what the rows. What do you call? This is rows. These are rows. So from 0 to 1 0, we are going it is one step. Similar way, so 0 to 2 0, we are going 2 rows, 3 rows, 4 rows, 5 rows. So is it right or wrong? This is the base case.
Sir,
Hello.
sir, but we have to write the number of ways in which we
No,
can
no.
go.
Is it right? But before it, how do you calculate? We required one status, Directly, how can you find it? I'm trying to
But
tell you how to solve it. Directly, how can you tell?
for these base cases, all the I mean, for all the columns, the lowest column will be 1 1 1 1, and for the all the rows it will be 1 1 1 1, because in only one way we can reach there.
Wait.
Yes, sir.
No. I'm telling this. This is that column positions. Actually, still it is not calculated anything. It's okay, but whatever you said, that inner value, I'll put it.
Oh,
But
that's the just positions. Okay.
positions. This is what maybe you can call it. It's I index position. This could
Okay, got
be
it, sir.
this could be Z. Is it right? Is
Yeah,
it right?
got it, sir.
Fine. So because it's a two-dimensional array we are creating, now let us we fill the base case basically. So base case means moving from this 0 to 1, 0 to 1, we require one step. Is it right?
Yes.
Similar way, from one this particular column to this column, we required one more step, because we consider it is one step towards right side, one step towards top. Similar way, here it is 1, here it is 1. Is it right? Is it
Okay.
right?
Yes, sir.
Similar way, we are moving from this place to this place. So that means towards up. One row we are going towards forward. One row, one row, one row, one row. Up to here it's clear. Is it right? So
Yes,
actually
sir.
to fill the base case, we required that index position J, index position I. These things are helpful. So because it's a two-dimensional array, what you call 2D array. Now my question is how to fill this one. So how to fill this one is very simple. See, to reach from 0 to 0 1, we required one step to reach. It's okay, no problem. That's okay. But now this is the index position of 1 1. Is it right?
Yes, sir.
Yeah.
This is the index position of 1 1. To reach from 0 to 1 1, how many different ways are there? Either you can go in this way, either you can go in this way. Is it right?
Yes, sir.
How many ways then?
2.
Very good. Two different ways are there. So either you go from 0 to 0 1, then this 0 1 to 1 1 I can go, either 0 0 to 1 0, then 1 1 I can go, either this way or this way. But how to calculate it? So how to calculate is very simple. What I do is to compute this current cell, how many ways to reach this particular position, how many ways to reach this position, how many ways to reach this position, how many ways. There is a standard calculation. What exactly this, to calculate this position, what I'll do is, let's we consider this is, this we call, different ways. What let you call this matrix name is M. What you call M. To calculate this ith one, what I do is simply the previous current I and j, to calculate it, I want to do that the matrix of I minus 1 j value, I minus 1 j value plus matrix of I and j minus 1. So what is this j minus 1, I minus 1 is? This I minus 1 is previous row. This is previous column value. So the previous column value, previous row value. So let's you take about this. Current ij is 1 1. Is it right?
Yeah.
Yeah.
So I minus 1 and j is same. So that this one we are getting. Similar way, I is this, previous j means this one, previous j. This is j minus 1. This is I minus 1. Am I right or wrong?
Yes, sir.
So these two sum we are calculating. These two sum we are calculating means this one 1 and this one 1 we are calculating. So what we are getting is these two sum we are calculating. These two sum, that means this is and this is we are calculating. This we are getting is 2. Similar way, these two we are calculating. 2 and 1. 2 and 1 we are calculating means 3. Similar way, this 3 and 1 we are calculating. This 3 and 1, 4 we are getting. This 4 and 1 we are calculating. 5 we are getting. Is it right?
Yeah.
Yes, sir.
So that what happens, to reach this 3, what are the different ways is either you can go in this way, or either you can go in this way, or either you can go, see, I can go in this way to reach this 3. I can go in this way to reach this 3. Either you can go in this way. Is it satisfied?
Yes.
Simple. So what we are doing is we are calculating current ij with previous I value and previous j value. So these two we are calculating. This is 3. These two we are calculating is 4. These two we are calculating is 5. In similar lines, if you go, what is the sum of these two? What is the sum of these two?
3.
Yes. Then what is this?
6.
This is 6. What is this?
10.
10.
What is this then? This part?
15.
15. Then what is this?
4.
But here there is a blockage area. Blockage area we cannot enter. Whenever you are not able to enter, it is 0. So we don't have that entry point. Once you have entry point, we can calculate something so that it will put it blockage areas as 0. So once it is 0, these two sum what you are getting?
10.
10.
These two we are getting is 25.
25.
So in this way we are going, this is calculated, this is calculated, this is calculated. So we are getting it is 5. Then it is 5 again. Sorry.
Yeah, 5.
5 again. This is 15 again. This is 40.
40.
Similar way, this is calculated. 5 and 1, 6 is calculated. This is 6. Then this is 11.
11.
This is 26. This it's going to be 66.
66.
Yes. So the right answer for this one, I don't know. There's a numerical type, I think. So how many paths is that? Answer is that it is 66. So most possibly we give it a simple grid. Maximum we go something like 4 cross 5 or 3 cross 4, something like that. And we'll give the blockage area. So even you can see that any quickly that summary code, if you could see that, yeah, here it is. Maybe, somebody wants to quickly refer it. See, grid is there. So what the initial is, so we want to go for directly dynamic programming. We don't want to look at this simple recursion memoization. Please look at here. So initially this matrix is there. All of the matrix values are zeros. So what they done is this I and j, whenever that zeros are there, that zeros, what do you call this base case they are trying to fill it. Initially what they are trying to fill it is I value and j value whenever 0 or 0 is found, that 0th row or 0th column. So all of them will be filled with ones, like similar way any barrier points they send it. Maybe some barrier points they'll give it. Thus barrier points also they are filling with 0. Of course, basically barrier points it will fill with 0, but anyway the barrier points we fill it that 0. Other than the barrier points is simple, like previous ith row and previous jth column, these two sum we are using to calculate that current one. So finally we print that matrix and right topmost value we are printing. So that is the thing, the right topmost value is the 66 is the different ways to reach from 00 to 45. So mostly don't worry, we don't give it a bigger dimensional array. Mostly we give it a smaller dimension array. Okay.
Okay, sir.
Good. So this is one standard problem. Basically, in any generally we ask from that week 9 means definitely we ask this way. And this is one more. Already I said longest common subsequence. See, if you could see that common subsequence is the commonality between strings. For example, let me take that Anil and Anup. So this is the two strings. So the common matched subsequence is that we want to find out it. The common subsequence we found is AN and AN. This AN and AN is the common subsequence. What you call, the similar matching thing. We are trying to find out that the longest common subsequence, how much length of common subsequence, which is a sequence. It's a sequential. There is no skipping of characters. Like AN and AN is a common subsequence. So that one we want to find out it. But make sure, please see the question. What will be the value of X? They are asking at this position, what is the value? At this position. They don't want the final solution. The final solution is at this position. The final solution we are getting at this position. Sorry, topmost one. No? Yeah, here it is. The final solution we are getting here. The solution is here. The longest common subsequence. But they are asking in the place of X. But remember, this kind of question definitely requires inductive structure. So when we are giving this kind of question, in the note we'll give it the inductive structure also, because we don't ask the student to remember this inductive structure, because it is a simple standard formula. So we don't ask you that remember yourself and then do it. Definitely we'll give in the note, please use the following inductive structure, then only you do it. So here also they clearly given that this particular matrix, how it looks like. The two strings they are given, A and B. Second string is AB. The common subsequence they want to find out it. It is very clear. We can say that common subsequence we are finding is that mostly it is A and B only it is matching. Am I right? A and B only, no? Is it
Yes.
right? So the possibility is the 2 only, but anyway, we'll try it. But whenever we are trying, there is an inductive structure is given, a mathematical inductive structure. So please see that this is the base case. This base case is, it is, we are trying to match this. This is null. Don't worry. What is this empty? What you call, none or null. This empty is called as none or null. Now let us we see that does null, is it matched to a character? Definitely no.
No.
Is it right? No. Similar way, again A. So that B, sorry, it's not matching to any of the characters. Similar with this none, they are trying, taking like, this one, this none. They're trying to match with this A, this B, this A, and this B. So that's the thing. They are filling these particular zeros is as a base case, because none never matches to that, another none character, because none means it's nothing character or null value. So we don't say that it is visible character also, what you call. So that's the thing. We say that base case, we are trying to fill it all up with zeros. Now the interesting inductive structure they're given. See that inductive structure? I plus 1, j plus 1. It's very simple. Whenever we are trying to do that, similar characters are found. This is called, similar characters. Similar characters. This is different characters. Different. Whenever similarity is found, what we do is the I plus 1, j plus 1. So we take that I plus 1 and j plus 1. So what is this I plus 1, j plus 1 as? What is that I plus 1, j plus 1 as? This it is the diagonal value. What this I plus 1 and j plus 1 is? This diagonal value. This one plus 1 we take it. Whenever similarity is found, whatever the previous value is there, that one plus 1 we do it. This is called, this is called diagonal value. Diagonal. Whenever you come to that, not equal things is there. Not equal things mean what is that, we are trying to find out I plus 1j, I and j plus 1. See, they are taking two different values. What they are taking is the bottom value, the right value. The bottom value means this, the bottom value. The right value means this. Out of that, which is the maximum we are trying to pick out at, that maximum we are finding it. What is this maximum is very simple. Whether first string is matching more matches in second string, or second string is matching more matches in first string. Hope you understand why it is maximum. Is it right? Hello?
Sir, can you repeat that?
Yes. So either first string, if you consider this is the st1 first string, this is the second string st2. So why do you take the maximum as whether the first string is matching more characters in second string, or second string is matching more characters in first string? Out of this, which is the maximum, that one we are taking. That is called max. Is it right?
Okay.
Understood?
Yeah.
So that is what, if it is matched, the previous matches plus 1, current match. Previous matches, already 2 matches are there. Third character is matched, plus 1 we do. For example, no matching is found. Whenever no matching is found, we try to take either first one highest matches are there, second one highest matches is there. That means comparatively first one more characters are matched with second character, or second character is having more matches with the first character. So that way we are taking in that which is the maximum we are trying to pick out it. That maximum is called bottom value and right value. This right value belong to this particular, this, first string and second string. And bottom values, we are taking that first string with second string. Now let us we take B and B. Is it matched or not matched?
Yeah, matched.
Whenever matched, we take this diagonal value. This diagonal value means, for example, this is that current index positions of this I and J we are taking. So let's consider, so if you consider that I and G index positions, this particular one we are trying to find out it, I plus 1 and J plus 1. So if this is current index position is 3 and 3, 3 and 3, this index position value I wanted, so 3 plus 1, 4, 3 plus 1, 4. So that means 0 we are getting, 0 plus 1. So what value we are getting here is, what value you are getting?
1.
1.
So that 1 we are getting. So this diagonal value plus 1. Similar way we are coming to here. Does B is matching to A? Is it matching?
No.
It's not matching, no. When it is not matching, this one and this one, out of this, which is the maximum? Which is the maximum?
1.
1.
So same 1 carries here. Next one. B is trying with A. Is it matching?
No.
So out of this, which is the maximum? 1 only. So 1 is the maximum, no? Now B is trying with A. Is it matching? No. Out of this maximum is 1. Out of this and this, which is the maximum. That's done. Now A we are trying with B. Is it matched?
No.
No.
So again, this is out of this, which is the maximum? 1 is the
One.
maximum. Now A we are trying with A. Is it matched?
Yes.
So when it is matched, the previous value plus 1, so that we are getting here it is 2. 2. So after that, A we are trying with again A, so that it is matched. Is it matching? No.
Yes, sir.
So previous existing matches plus 1, so that it is again 2. So after that, A we are trying this way. So A we are trying A, again it is matched. The previous diagonal value plus 1, so that it is getting 2. So up to here it is done. Now we are trying with B. This is over, this is over. Now B and B is matched. Whenever B and B is matched, the previous diagonal value plus 1, it is 1. After that, B and A is trying. Is it matched or not matched?
No.
Not matched. So that still now matches are 2. Now B we are trying with A. Is it matched or unmatched?
No.
Not
No.
matched. Not matched means out of this maximum 2. So that current value is 2 only. So current X value they are asking, X is 2 only. But still we are going, what happens? Actually, final solution also we are getting 2 only. We'll try to what is there. So after getting this, again we are trying with B and A. It is not matched. When it is not matched, out of these 2, maximum is again 2.
Sir,
Tell
so
me.
that should be 1.
Hello?
No, sir, okay. It's,
Yeah.
it's correct.
So now A we are trying. A it is matching with B, not match. Out of these 2, 1 is the maximum. This one and this one. Then A we are trying with A. It is not, it is matched, sorry. It is matched means this one plus 1, so that we are getting 2. So A we are trying with A. It is matched. Out of this maximum is again 2. A we are matching with A, so that final value is 2. Only till now the matches are only 2. Because it's a continuous matches, longest common subsequence word.
Sir,
This
for
will
the
be 3, right? This
Yeah.
A that below 1.
Where
That
is
should
that?
be 3, right? So
the
that
0,
A is matching
1.
with A. 0, 1.
Wait. Sorry. I'm sorry. The last one you're asking about? This A. Yeah, this
Yeah.
A. Yeah. You're right. So A is matching with A. I'm sorry. Yes. You're right. A is matching with A. This is matched means this one plus 1. So previous value plus 1. So that it's 3. And after that, again, A and A you are trying. This is, 3. Actually, you're right. Correct. So the common subsequence means the A is matching with 3 sequences in the first string. Is it right? Yes, you're right.
Yes.
Correct. So it does not mean that A is having a sequence of attest rich 3 characters matching. This could be first string. First string, A character is matching 3 sequence of characters in the second string. Yeah, you're right. Perfect. Thank you. But here the X value they're asking, no, X value means this 2 only. But final value is 3. Final value is, yes. But inductive structure, we strictly give it because, these kind of complexity problems definitely will give inductive structure, because dynamic programming, we try to ask the student how to solve it, but inductive structure we'll give it prefix with that. Okay.
And
you
sir,
understand?
for finding the actual longest common substring, we'll trace back on the diagonal.
No. Last top left corner value is our solution. If you have started from
Yeah.
bottom up, that is.
Yeah. No, but if we have to find the actual substring,
Mhm.
I mean, if whether it is AAB or AAA,
Mhm.
so for that we have to start with this 0 column,
Mhm.
0 entry, and
Mhm.
trace back diagonally, right?
Yes, diagonally only.
Okay.
Yes. Just give me 1 second. I'll switch on that power. There's low power in my laptop. Just a minute. So this is one standard problem which frequently we ask it. And
Hello, sir.
yeah, tell me.
Sir, here I and J is the base case, or it is above that?
Base case only. See, we already filling that base case of that I index position and J index position. This is I, this is J. See, even you can see that the base code, if you would like to see the summary of it, LCW. So subword, this is different. LCS, yeah, it's a common subsequence is this. Yeah, here you look at it. So initially this matrix is filled with zeros, because one additionally we are taking. If you could look at, additional row is created. As I said, it is null character is there, no? Is it there?
Yes, sir.
So similar lines we have filled it. After filling it, we are trying to check it whether it is equal or not. Whenever equal character is found, of course here it is I and J they are taking, instead of it they are taking C and R. Maybe just changing the name of the variable is okay. But remember, whenever similar characters are found, what we are trying to do is we take the diagonal value plus 1. Is it right? Okay. Hello.
Yes. Yes,
So
sir.
whenever different characters are there, whether we take that rightmost value, that means it is from the first string, rightmost value, or second string bottom value. So like, C plus 1 or R plus 1, either row plus 1 or column plus 1. Out of this, which is the maximum we are trying to pick out at that pickup value, the maximum we are putting. Then the final solution is available in top left corner. That is we have filled it, uh, bottom up filling of, solution is bottom up. We are trying to find out. So actually this session, even you can see that complete session. Of course, actually coding is not much important, because you are attempting enter means it is only numerical type or MSQ or MCQ. Yeah, ask me something else. You want us something?
Yes, sir. About this question, so
Hmm.
previous question,
Hmm.
sir, in previous question, that was asking for the number of ways.
Hmm.
So it's a
Hmm.
kind of probability type question. So is there any other way to solve this?
No, no, it's not probability actually. There is a standard approach is a dynamic programming, but we don't ask you that a big grid. Like if you could see that in summary, there is a bigger grid was given. Like the grid path is very this is it right? There is a grid of that 0 to 5, 10, 5 rows and 10 columns. Is it right? Hello.
Yes. Yes, sir.
But in the question paper, we don't ask you such a bigger grid. We'll ask you that very smaller one, something like this, like 4, 4, 3, 4 size. Maybe we give it more blockage areas. Okay. Generally,
Yes,
we
sir.
found it that way. Don't worry, it is probability way we have to go. The standard approach is using this, calculating I minus 1 and j minus 1. These two plus we are calculating to compute the current path. Like to compute this 15, we try to use this value and this value to compute the current value of 15. So I minus 1 and j minus 1. Okay.
Yes, sir.
Sir,
Hmm.
sir, how the longest common subsequence is 3? Like it should be 2 now. Like AB
No.
is
See,
only
there are
matching.
two combinations are there. See, LCW is there, LCS is there. Please look at it's a word. LCW subword. Is it right? LCW. So are you finding my screen?
Yes, sir.
So LCW is the common subword where it is a word. Here LCS means skipping is allowed. See, can drop that some characters. So when dropping in that case, so this A is found at a sequence of this A. Did you understand?
Yes, sir.
So, but in the case of subword, what is that when AB should be exactly matched in the same sequence, like AB should be in a single attestation. We don't have bypassing. Understand it?
Yes, sir.
Okay.
Got it.
B is there. This B, it is found 2 times in this one, but this A, it is found 3 times in this way. So that longest common subsequence, it is subword, it's not subsequence. So subsequence might have dropping of words or dropping of characters are there, but it tries to find out that match wherever A is found 3 times. First string A is found, second string 3 times in the second string. So that you can see that there is just they are talking about. Whenever LCW it is different. LCW it is different, where it is a common subword. It's a subsequent subword. LCS subsequence. Okay. Yeah.
Sorry, sir,
Hmm.
could you show the difference in the code?
Yeah, code. See, it is. Don't look at the code. Please look at this inductive structure.
Yes.
So whenever similarity is there, so I plus 1, j plus 1 is okay. Same, no? Is it right?
Yes.
So in this case, LCS also same. LC is also same. But plus 1 they are taking. So here it is plus 1 also taking. Clear?
Okay.
But
when they are
whenever
different,
different is there, see, whenever different characters are there, whatever the previous values are there, all of them resetting to 0 because LCW.
okay.
Because bypassing or dropping is not allowed. But here dropping is allowed. That's the thing. Out of that, which is the maximum? Whether first string more characters are matched to second string, or second string more characters are matched to first string. Out of that, which is the maximum? That one we are taking and we are going on with that maximum. Yeah.
Yes.
Yeah.
Sir, I have one more question. When we do the coding, there we were creating np dot zeros, right? So basically, we're creating a matrix of zeros.
Yes.
So when we do LCS, say x comma y in square brackets, are we really accessing the matrix? Because matrix is just a list of lists, right? So
Yes. It
do they have to
overwrites.
be in their own square bracket?
It overwrites. Already zeros are there, it will overwrite. It will consider only that bottom level zeros only, base case values only. Remaining values are overwrite.
No, my question is more in this sense that when we write LCS I plus 1 comma j plus 1 in square brackets, shouldn't we write them in separate square brackets?
Yes, that is a coding standard because Python it takes that LCS of I and j. Is it right?
Yes.
But in the mathematically they are representing in this way. No worries. It's a
Okay,
coding
because the
syntax.
code also gives
Yes,
this.
coding. This is coding syntax. Yes, you're right. Okay.
Thank you.
In the code we use numpy, that's why we write in this form.
Exactly. Correct.
Okay, so we can write in this form if we're using numpy.
Yes. Please look at it in numpy because numpy array is different. Normal list is different. See, this is a numpy array. This is not a list of lists. It's a
Okay, so
it's a numpy array. So
okay.
array as that without a list of lists, simply you can give comma separator. If it is list of lists, we have to give it two subscript operators, two square brackets. Okay.
Yes,
Yeah.
got it. Thank you.
Yeah, this is one more interesting question. But before going to the question, hello.
Sir, just
Yes, sir.
Somebody wants to ask something?
yes, sir. Sir, in this matrix, suppose we say 1, 1, that is A and B. So it is, so that count is the number of matches until this letter, right? From
Exactly.
A and A B A B B A
Yes.
B. Yes.
Yes. Until that character. That's it.
Okay, how many are matching?
Yes. How many of them are matching, and which is highest? Maybe first string matching highest matches with second string. Second string matches are highest matches with first string. Maybe out of that, which is the maximum.
Yes,
Okay.
sir. From this side to back.
Okay. Yeah. So edit distance directly. Actually, this one is a direct question that I've asked you to avoid that, time consuming process. But quickly, if you want to understand this, edit distance is converting one string. Let you take string 1 to string 2 with number of edit operations. So the edit operations includes updating values, deletion, addition of characters, like adding of characters, like converting first string to second string. So how many characters you need to add it, how many updates you need to do it, how many deletions. These three operations are called as edit operations. What do you call, edit distance, to convert a first string to second string. For example, even you talk about that Anil and Anup. To convert this Anil to Anup, how many edit operations you need to do is, this I and L is there, no? This I and L is there, is it right?
Yeah.
It has to be converted into OOP. So what I should do is, two updates I need to do, is it right?
Yes.
I and L has to be stored, replaced with O over O, plus one adding of the characters I need to do. Is it right?
Yes, sir.
Yes.
Similar way, Anup I want to convert into Anil also. I should do that. Again, what I should do is, two updates I need to do. Still, what should I do? Plus,
One delete.
yes, one delete operation I need to do. This way I want to calculate it. In this way, if you want to do that, this Monday has to be converted into Tuesday means simply I can calculate. Actually, edit distance between two strings is, there is a induction is given, but before giving induction, simply if you want to calculate this Monday to convert into Tuesday, so what I supposed to do is, this day is no problem, do not do anything. This MON has to be converted into Tuesday, so what I should do is, 3 updates plus 1 addition of characters. Is it right?
Yes.
This is Monday to Tuesday. Similarly, Tuesday we want to convert into Monday. I supposed to do 3 updates.
1 deletion.
Yes, 1 deletion. This usually you are doing, like, simply we are doing by a simple string, like this Monday and Tuesday, easy to understand. This Anil and Anup. Generally we give in this way, but sometimes what we ask is, we give a complex string, like so find out the edit distance between two strings. So in that case, again you have to look at that, the inductive structure. See, look at your inductive structure, edit distance. This is edit distance. So here also we take the strings like, secret and bisect is there. To convert secret to bisect or bisect to secret, how many edit operations I need to do? So for that, there is a inductive structure. See, look at here. the similar characters are found. If you could see that the inductive structure is, if similar character is found, what I supposed to do is I plus 1 and j plus 1. I plus 1 and j plus 1 means it is a diagonal value. Is it right? Is it right?
Yeah.
So diagonal value we take it, or we take that, we take the three values. See, we have a combination. Diagonal value, the edit distance of diagonal value, and so I plus 1 and j, what is, I plus 1 and j means it is the rightmost value, and
Yes.
I and j plus 1, which is a bottom value. So what these are, these three are, I supposed to write it, this inductive structure is here, just a minute. So I'll write the inductive structure as the matrix of I plus 1 and j plus 1. This is first matrix, and next one is I plus 1 and j. Next one is the matrix of I and j plus 1. If you could look at these three minimum we are extracting, minimum. So please look at that, minimum 1 plus 1. So plus 1. So for example, if you take the grid, in this grid, so you can see that, for example, like this could be your grid. Maybe, edit distance you are calculating. So whenever equal characters is there, no problem. Earlier, whatever that, inductive structure, what is there, same thing. To calculate this current value, what I supposed to do is, I supposed to do the three values combination, these three values. Like, I plus 1, j plus 1. This is I plus 1 and j plus 1. I plus 1 and j, I plus 1 and j is this. And I and j plus 1, this. These three minimum we are finding, this minimum plus 1. This minimum. So earlier, how many additions are there? Plus current editor. Understood that? Converting the first string to second string. Maybe you require,
Yes,
earlier changes are required as earlier edit operations are 2 plus this current edit operation. That is what plus 1. Earlier edit operations are 3 are there. So what are the 3? Either first string requires highest additions, second string requires highest additions, and the previous additions are there, whichever, what you call, diagonal value, the base value. Out of this, which is the minimum one, that minimum one plus current addition, current edit operation, what you are doing. So out of these three, that's one thing this inductive structure will help you. But generally, whenever we are giving the inductive structure for edit operation, like edit distance calculation, we give simple string. The simple string in the sense, like what I said, Tuesday, Monday, Anil and Anup, IITM and IITB, so something like that. We try to give the question in that way. If any case we try to give a complex string means, definitely we specify this inductive structure also. Whatever the previous question we got it, similar lines we go with the inductive structure for this one. But the current answer is this one is 4, because 4 operations we need to do. Either 3 updates and 1 add, or 3 updates and 1 delete. So that's what converting first string to second string. So hope you got it.
yes, sir.
Fine.
So we take minimum means like whether converting Monday to Tuesday is having minimum steps, or
Yes.
Tuesday to Monday.
Yes. So
So we take
whichever, currently this smaller string and higher string is okay. But for example, equal length of strings is taken. Yeah. Equal length
Yes,
of
sir.
strings is taken. Then we are trying to convert it. To convert the first string to second string, either first string operations required second string, like Anil, Amul, AMUL. Let me try this one. ANIL. Maybe Anul, you try it. What is there? So in this case, what happens, A, M and N is there. Only one addition operation I need to do, one replace operation. So
Yes, both are same.
Both are same, only one character is same. One character is different. That addition operation, just one replacement is enough. So we are trying to take the minimum plus current addition. Current addition in the operation is required. Whenever equal is there, we don't do any case. Just simply we get the previous value and we keep going. Yeah. So please look at the inductor structure, but we don't give it the edit distance with a complex string. If you give it a complex string, definitely we specify that inductor structure. It is easy string we have given, so that we directly ask you to calculate simply by brute force effort. What you call brute force effort. Yeah. Yeah. So this is one more interesting thing about dynamic programming problem. The matrix multiplication. See, actually, basically, before directly we jump into this question, please remember multiplying two matrices. The basic condition is first matrix columns must be equal to second matrix rows. Is it right or wrong?
Yes, true.
Yes, sir.
This is a standard compatibility. What you call, matrix multiplication is possible if and only first matrix columns are equal to the second matrix rows, because each element of the column we are extracting to the first matrix and we try to multiply that each element of the second matrix and we do the addition. Is it right?
Yes, sir.
So that is a basic standard. So based on it only the question is framed. Please careful about it. Remember M1, M2, M3, M4, the sizes they have defined, like the matrix dimensions. P and Q is the first matrix, Q and R. See, these two are equal. Similar way, Q and R is there, R and S is there. So similar way, R and S is there, S and T is there. So what they want to tell you is the M1, M2, M1 columns are equal to M2 rows. Are you understanding?
Yes.
Similar way, M2 columns are equal to M3 rows. M3 columns are equal to that M4 rows. So that's a basic thing. Where PQRS are distinct values. How many ways to evaluate the product of M1, M2, M3, M4? Remember, let you take it. Each step we are multiplying two matrices only. What does it mean is, you have a function called multiply. This function takes only two parameters like A and B. A is a first matrix, B is a second matrix. It is not capable to take three parameters because at a time it can do multiplication of two matrices only. That is a limitation. That's what they want to tell you, that multiply the two matrices at a time. Each step we are multiplying the two matrices only. So how many multiplications are required? See, if you could see that, like you take directly, we don't want to go for 4. We take three matrices. 3. How many ways to multiply this? So 3 matrices means M1, M2, M3. So let you take that first way of matrix multiplication is, your function takes at a time two particular matrices only, So maybe your function name is function, which takes that M1, M2, then whatever returned value is there, that we are multiplying with M3. Is it right? Is it right?
Yes.
yes, sir.
This is first way. Another way is there. Same function. We are trying to do that M1, M2, M3. First we multiply these two. Whatever the result we got it, then we try to multiply with M1. This is the second way. Is it right?
Yes.
So totally two different ways to multiply. Two different ways. Now let's take 4 matrices. 4. M1, M2, M3, M4. How many different ways are there? Now let's try the first way as M1, M2, M3, M4. So it's a direct one. First we are multiplying these two, this one, and then this one. So this is the first way. Second way we are taking one more, M1, M2, M3, M4. So first we do that multiplication of M1 and M2. So these two. Then we multiply that M3 with whatever the result we got of these. Then we multiply that whatever the result we got it with M3. Then with M4. So we got that another way. The next way we are taking M1, M2, M3, M4. So in this case, what we do is, first we are multiplying that M2 and M3. So whatever the result we got it, that M2 and M3, we try to multiply with M1. Then whatever the result we got it with this M1 and M2 and M3, we multiply with M4. This is another way. So hopefully I'm expecting two more. Yes, it's two more, I think so. Let you try that one more. M1, M2, M3, M4. So now let's try now M3 and M4 first, because columns are same. Then whatever the result we got it, that we multiply with M2. Is it right? Is it right?
Yes, sir.
Yes, sir.
Whatever result we got it after M2, M4, M2 is multiplied. Then we multiply with M1. So we got it one more. Oh, finally we get it one more. Let me try that one more. So what is the one more is M1, M2, M3, then after M4. Okay. Now what we do is M1, M2 we do. Then we multiply with M4 because that combination is not done. M2, M3 we done. Then we combine with M1. M2, M3 is done. M4 we are multiplying. Then whatever the result we got it with the M1. So that it's another way. So totally, sorry, another way. So totally 5 different ways to do. 5 different ways to do. Generally, we ask that at most 3 matrices only. We don't ask more than 3 because we don't ask you to that verify all the different ways. Like maximum we ask that 4 matrices. So the 4 matrices means maximum we get 5 only. But there is one more type of question. Possibly you get it. So let you tell you that what is the one more question on the matrix multiplication only. Possibly you get it this way. Another type of question, same concept, another type of question. What they're asking is they will give you a matrix. M1 size is 2 and 3. M2 size is 3 and 10. And M3 size is 10 and 2. The question they are asking is which order of multiplications, sorry, which order of matrices multiplication will result minimum number of multiplications. Minimum number of multiplications. That means first we do M1, M2, then M3, or M2, M3 we do with M1. So that way we have to find out it. So is it okay? Hope you understand the question. What they are asking is another kind of question is. Okay.
Yes, sir.
Either you multiply M1, M2, then the result we multiply with M3, or M2, M3 we multiply, then the result. Now let us we try the first ways, because 3 matrices means only 2 ways are there. First, let us we do M1, M2, then with M3. So we try to do this multiplication first. Then the result what we are getting is we are multiplying with M3. If you do this, how many multiplications you require? No, this is 2 into 3 multi, 2 into 10 multi, because 2 rows, 3 columns, 3 rows, 10 columns. So total multiplications is 2 into 10. Is it right?
Into 3.
Yes.
So into 3 also now. 2 into 3 into 10.
Wait. I did it M1, M2 only. Okay. After that, when M3 is added, hello.
So it will give us the row, like the matrix of 2 rows and the 10 columns.
Wait. What? Hello. So here it is. Two threes are there. Sorry. I'm sorry. It is doing, yes. These are, yes, correct. 2 into 3 into 10, exactly. 2 into 3 into 10, because 3s are common. Is it right? Hello.
Yes, sir.
So that what happens,
Yes.
this is 2 into 3 into 10. These multiplications are 60. Now this one plus this particular, whatever the result we got it, is that 2 into
2 cross
10, 2 into 10 we are getting. Is it right? The result we are getting 2 into 10. So the 2 into, hello.
Yeah.
The result 2 into 10, no, we are getting, no. This result we are
Yeah,
getting
the matrix size.
2 into 10, no, size we are getting.
Yes.
Yes, sir.
This 2 into 10 and 10 into 2, what exactly is 2 into 10 into 2? Is it right?
Yes.
Yes.
So this number of multiplications are 40. So here it is, total is 100 multiplications. Fine. Hello.
Yes, sir.
Now another way is there. Another way of multiplication. Now we'll try another way of multiplication is M1, M2, M3. First we multiply these two, then the result we are multiplying with this one. So what it is happening is, we are trying to do that 3 into, let me check the size. Yeah, 3 into 10 into 2. This multiplication is 3 into 10 into 2. So what you get it as 3 into 10 into 2. These multiplications are 60. Is it right?
Yes.
So, but the matrix size we are getting is the 3 into 2 only. Fine.
Yeah.
Hello? Yeah. Now 3 into 2, then we are trying to do with 2 into 3. Is it right?
Yes.
So that this one plus 2 into 3 into 2. Whenever this result we are trying to multiply with M1. So these multiplications are 2 into 3, it is 6 into 2, it is 12. It is 12. Total it is 72 multiplications. So the minimum number of multiplication combination is this. First we multiply M2, M3, then we multiply with M1. So generally we give it, this could be, MCQ question. Like we give a combination of M1, M2, M3 with different sizes. We give it, this combination is, which of the below is that, least number of multiplications or highest number of multiplications. There is other way of asking the question in this multiplications. Possibly we don't give more than 3, and simple sizes only we give, like 2 into 3 into or 3 into 5, something like 3 into 2, some smaller size of matrices. Yes. Only we give it. We ask you to find out with a sufficient time. We don't ask you that 4 or 5 matrices and get it done minimum number of multiplications. This is another question possibly we expect from this concept. Hope you got it.
Yeah, got it.
Yeah. So in the exam we don't have to consider matrix, right?
No.
For multiplication.
No. We do not. Just only The minimum number we ask it, otherwise how many number of total combination of multiplications possible. That's it. We don't ask you that matrix multiplication result or something. Okay. Yeah. Just give me one second. Get back just a moment. Yeah, thank you. So this is the fifth question. Yes. Sorry, this could be the
I have one.
Hello.
I have one question. May I ask?
Yeah, tell me.
On this matrix multiplication, there also is this kind of logic is available, no?
Which one?
Like you showed for if this I is matching with J, that kind of logic is there. That kind of questions comes.
No. I is matching with J means columns and rows. You're asking?
Yeah, those kind of logic things. Does it come in question paper?
No. In the matrix multiplication, only two ways of questions. There is no inductive structure. No, you're asking about inductive structure. Is it right?
Yeah.
Inductive structures are not there in matrix multiplication. Only they'll ask you that 3 or 4 matrices. How many ways to multiply? Otherwise, 3 matrices. What is the minimum number of multiples? There is no inductive structure for matrix multiplication. But for these problems, there is inductive structure. We ask you. We don't, we give you inductive structure and we calculate. We ask you to calculate. Clear?
Okay.
Yeah.
So for matrix multiplication, we don't need a DP grid. Right?
No, DP grid not required. We don't ask you such complex DP. See, DP grid calculation is something complex in matrix, so that we never ask. Even you check it the previous year questions. Possibly we don't give it. At most we give it inductive structure along with it, edit operations, longest common subsequence, grid path. That only. In the matrix, we give mostly simple question only. We ask you that. Okay.
Yes, sir.
Yeah. Grid path, we inductive question we don't ask you in the matrix. Yeah. So up to here, the dynamic programming. See the lucky, you can say that easiest thing of that week 9 is the week 9 is very difficult in the case of OPP examinations, because OPP examinations, whenever there is a problem is given, you need to figure out the solution with a clever recursion. Otherwise, you have to apply the bottom-up approach of that dynamic programming, so that there is no limit. What you call the week 9 in the OPP examination is they might ask you that any kind of problem in the dynamic programming, you need to find out a clever solution of clever recursive algorithm. Is it right?
Yes, sir.
But in the end term examination or quiz examination, there is a questions of MCQs, which are that MSQs are there. They are pretty straightforward. They will give you the clue. They will give you the inductive structure. Directly we ask you the standard algorithm only. We don't ask you new problem. Definitely we don't ask you new problem. But in the OPP examination, definitely we ask you new problem. That is what the thing. So you can directly answer. That is very easiest thing. Even quiz examination, when you compare with OPP examination, that is what the easiest thing. If conceptually you are strong, you can easily achieve the good grades in that. Yeah. So now the week 11. So when just quickly, if you recap that week 11, basically the week 11, it belongs to the concepts of linear programming. Basically, generally the week 11 does not have any standard algorithms. All of them are only the classification of problems. Week 11 is completely classification of problems, which they don't have no standard algorithms. Is it right? Only mathematical models are there. Just if you could see that,
yeah,
the previous live session or something like Professor Madhavan's lecture, you can find it. No standard algorithms. First approach of this week 11 is linear programming. So then we are going with network flows. Network flows we are going. So then we are going with, reductions, what you call, one problem can be reduced to another problem. And the final one is classification of algorithms like NP, NP hard, NP complete, and polynomial. Classification of algorithms. See, all of them are generic problems. Generic problems means we don't have any standard algorithms. Generally, we have theoretical concept only. Still, there is a research is going on. The researchers will preserve their work in terms of, any particular algorithm can be achieved with a polynomial time, something like that. Now, let us see the sixth question, which is somewhat interesting question. Please look at here. There is a graph. There is a graph. The graph which we are taking, any kind of graph, maybe you can take it. Here you should understand the minimum vertex cover in the graph is 12. The maximum independent set in the graph is 70. See, to understand better, again I'm recapping Professor Madhavan's lecture. He has given a graph. In that graph he said, whenever a discipline committee is formed, like he said, good example, very interesting example. If discipline committee is formed in a particular educational institution, they want to form a discipline committee with a combination of one mechanical professor, one CSC, one electrical, one civil engineering. The reason is simple. They don't know each other. Is it right? They don't know each other. So they are independent. What you call, independent. In the discipline committee, if 2 members are from CSC, 2 members are from mechanical, so the other members are not there. So maximum favor, it goes to that mechanical department. So that's the thing. He has given one good example. That is what maximum independent set is said. Similarly, he said about minimum vertex cover also. Minimum vertex cover means, he said one example of CC cameras. Whichever the particular vertex is covering the maximum edges, minimum cameras we are trying to fix it, but it will cover maximum edges. That is called, minimum vertex cover. Anyway, I'll go with one graph also. So please look at this graph. I'm going with the graph before solving this question. Just I'm taking a simple graph. 1, 2, 3, 4, and 5. To understand the concept, actually, it's a straightforward question, but to understand it, I'll tell you what exactly this one. Actually, you not draw the graph also. It does not mean that you need to draw with 12 vertices and 17 vertices. You not do it, just to understand better. So this is one graph. Let you take one example. 3 nodes to 2, and 2 nodes to 4, and 2 nodes to 5 also. 4 nodes to 7, and this is 5. 6 knows about 7, and this knows about this. 3 knows about 7. Let you take this. This is one graph. So now, let me see that. What is the maximum independent set? So I want to make that independent members in the discipline committee. So I want to do the maximum independent set. So let you do that. Independent set is, I can consider that this 1, this 4, this 5, and this 6 as independent set. This is independent set. How can you say the independent set as 1, 4, 5, 6? Does 1 knows about 4? Is it connected 1 and 4? No. 4, is it connected to 5? No.
No.
5, is it connected to 6? No. So it is one independent set. Is it right?
Yes.
There is another independent set also you might have. This is another independent set as what you call, ID set to understand very easily. 2 and 6. Can you make 2 and 6 as independent sets? This 2 and 6?
Yes.
If 2 is made as independent set, can you make 1 as independent? No.
No.
Is it right? Hello?
Yeah.
If 2 is made as independent set, can you make 1 as independent? No. 3 as independent?
No, we can't.
4? No. 5? No. But 6 we can do. 6 we can do. If 6 we do is independent, we cannot make 7 as independent. So another independent set I can create. Can you tell another independent set? Other?
So 3, 4, 5.
7.
Exactly. 3, 4, 5. Similar way, other independent sets, anything?
2, 7.
Yeah, 2, 7. Next, one more. Anything else?
1, 7 also.
Yes, 1, 7. Now, out of all these, what is the maximum independent set?
1, 4, 5, 6.
Exactly.
1.
I want
5.
to include maximum number of departments involvement in the discipline committee. So that is called maximum independent set. So we got the maximum independent set is 4. That is here, the maximum independent set of the graph is 17, they said. So they might have a graph in that independent set maximum size is that 17 is available. Now, minimum vertex cover. So what is the minimum vertex cover is? If you fix a particular CC camera for a particular vertex, it will cover maximum edges. It will cover maximum edges. If you consider in this way, if I'll fix a camera here, it will cover 4 edges. Is it right?
Yes.
Similarly, if I'll fix a camera here, it will cover another 4 edges.
Yeah.
Is it right? Similarly, if I fix that another camera here, it can cover that maximum edges. By using 3 cameras, does all the edges are covered or not?
Yes, sir.
Yes.
So this is 3, 2, 7. So minimum cameras are 3. I can cover that all of the edges. For example, you try the camera for 5, it will cover only 2 edges. I'll try that 4, it will cover 2 edges, and then I will use it another camera for 6, it will cover 2. Still 7 is not covered because 7 to 3 is not covered. I need to fix that another one is 7 camera here. I need to fix the one. So here totally 5 cameras we are using. It is maximum vertex cover. We don't want it. We don't want to increase my expenditure. I want to do less expenditure. I want to cover all vertices. So this is minimum vertex cover. Is it right? Hello?
Yes.
Please look at the interesting thing is the maximum independent set vertices plus minimum vertex vertices. If you do these two sum, we get that graph sizes. Understand?
Yeah.
Yes, sir.
So here 1, 4, 5, 6 plus 3 to 7 is my total size of the graph. So the total size of the graph is nothing but minimum vertex cover plus maximum independent set. Maximum independent set. This is a direct straightforward, but to prove it, the professor is given excellent one graph and he has shown you this one. So now what is my number of vertices in the graph? Answer for this one?
29.
29.
Exactly. This is 20. Yes, it is straightforward. So this is one interesting question. Actually, to prove it only, the professor is given one example, but a general straightforward is to know that number of vertices in a graph, if they will give it minimum vertex cover value, maximum independent set. Simply we try to calculate the sum of these two, we get that how many number of vertices are there in the graphs. This is one straightforward, but anyway, to understand better. Actually, Why should I tell you this one is sometimes we'll give it a graph and we'll ask you that what is the minimum vertex cover. Find out that there is a multiple choice questions we give it. At that time, you're supposed to identify which of the particular vertices are covering maximum edges. That set you need to select it. Similar way, independent set also will ask you maximum independent set. So which are, the set we are selecting is independent, and that to maximum number of vertices has to be involved. The discipline committee has to have the different combinations where all the departments are involved. That is what our objective. Yeah. Okay. Is it clear?
Yes, sir.
So the sum will always be equal to the total number of.
Exactly, definitely. But this is direct question. But whenever we want to give other kind of question, the same concept, we'll give a graph. We'll give a graph and we'll give you the choices of that. Identify the right maximum independent set below A, B, C, Ds. We'll ask you that identify the minimum vertex cover in the ABCD. So we need to select that which one is the minimum, which one is the maximum. There are possibility of 3 different questions in the same concept. Clear? Okay.
Yes, sir.
Yes, sir.
Yeah. This is, I said, the week 11 is having that one mathematical modeling strategies are there. In that one, another example is linear programming. So whenever linear programming concept, if you recollect, there is a scenario is given. Generally, if you could look at the week 11 live session or Professor Madhavan lecture, the basic problem, they will start with a sweet shop with 2 combination of sweets that is extended with 3 sweets, actually, 3 combinations. Some constraints are there. In the linear programming model, always variables are involved, constants are involved, and constraints are there, some kind of conditions. Using it, we are trying to achieve objectives. Is it right? Is it right?
Yes, sir.
But in the solving of that linear programming model, definitely it is a exponential solutions only, because even you can check it, the sweet shop problem, or it might be 3 combination of sweets. We try to draw one particular 2-dimensional graph, a 3-dimensional graph. We try to identify that linear approach of feasible area to identify that linear, whichever the combination is a profitable combination. Definitely it requires an exponential combination, but there is no other way, because it's not a standard algorithm, always mathematical. But we don't ask you such questions. We ask the questions on variables, constants, constraints, and objects. So we give a real-time scenario, we ask a question. So please look at the scenario. We don't ask you that what is the profitable combination. We never ask you, because calculating a profitable combination is a exponential solution. We have to find out is a time consuming process. We possibly, what we ask is, we ask you the questions on variables, constraints, and all. So please look at here. There is a generalized question, real-time scenario. There are 2 kinds of cakes are there. First kind of cake requires 200 grams of flour, 25 grams of fat. Second kind of cake is there. It requires 100 grams of flour, 50 grams of fat. So that is, 2 varieties of cakes. So formulate the linear programming model. We need to formulate linear programming to find the maximum number of cakes made from 5 kg of flour. See, there is a limit in the store. In the bakery store, we have only 5 kg of flour quantity. Flour is available, and 1 kg of fat is available. So assume that there is no shortage of other ingredients. Other ingredients may be sugar. All these are sufficient available. We don't worry about it. But there is a constraint is there on flour. There is a constraint is there on the fat. Did you understand? So using it,
Yes,
they are making the cakes. 2 varieties of cake they are making. The above problem is to be formulate a linear programming model let us X and Y are the number of cakes of kind first and second. So X is nothing but first kind of cake, one type of cake. Y is nothing but second kind of cake. We have a combination. Which of the following is not a valid constraint? Valid constraint. Constraint means checking conditions like less than, greater than or equal to something like that. So please look at here. We are taking valid constraints, no? X kind of cake, Y kind of cake. Very quickly we can do it. There is a floor which is required for that X and Y. The floor required for this one is 200 grams. It requires that 100 grams. Similar with fat, it requires that 25 grams. It requires that 50 grams. Remember, they have given the limit 5 kg of flour and 1 kg of fat. Let me convert this 5 kg and 1 kg into thousands, because here the grams are given, here it is kilograms. Is it right?
Yes, sir.
Right? Equal units we try to convert. Once we convert into the equal thing, what we trying to do is, we supposed to formulate one particular constraint. So one constraint that is common constraint for X and Y. You can make using 200x, that means X means the number of cakes, plus 100 what you call Y, which it must be less than or equal to 5,000 grams, because 5,000 grams. Why should it's 5,000 grams? It's a 5 kg.
5 kg is available.
Yes, 5 kg. We are converting into that 5 kg into grams. This is the constraint of flour. Similar way, another constraint is there. Another constraint. So that constraint is 25 grams of X, and we are using that 50 grams of Y, which is fat constraint. Where in the store the limit is 1,000 grams. We should not exceed this. This is that fat constraint. Is it right? Hello.
Yes, sir.
So let us be simplify this. So what they are trying to do is, if you simplify this one, we can simplify this. We can make it 50. We can make it, it's a 2. So that 100s ones we can convert, 100 2s and 100 50s. Okay, over. So 2x plus y less or equal to 50. Is it right?
Yes.
This floor constraint is okay, no? Using 50 grams of what you call flour, 50 grams of flour, we can make that 2 into x cakes plus 1y, which is less or equal to 50 grams of flour. Is it right?
Yes.
Yes.
So can you make this constraint is true?
Yeah, it is true.
It is true. Fine. Now we try this one. So 25x and 50, again we do the simplification. So in this way, if you do it, this 25 2s are we can do, this 25 40s we can do. Clear?
Yes, sir.
So that x plus 2y less than or equal to 40 grams of fat. Yes, it is possible. It is possible, no?
Yes.
Yes, sir.
Now,
Yes.
there is an implicit constraint is there. Even in the professor lecture, the linear programming, we don't have a chance of carpets manufacturing. Implicit constraint is no negative carpets. Similarly, there is no negative sweet boxes. Implicit constraint is definitely 0 and above. So that x value should be 0 or greater than 0. Y value should be greater than or equal to 0. So this can be possible. Is it possible, no?
Yes, sir.
Yes, sir.
Now, this combination is possible or not, we'll try. X plus 2y less than or equal to 50 is possible?
No.
No.
No, sir.
X plus 2y less than or equal to 50. Either you can check floor constraint, either you can check fat constraint. It is not matching. So invalid constraint we are trying to find out. This is not a valid constraint. Either you can consider either fat or floor, it is not matching. So this is one kind of question. See, generally what we give it, these kind of questions we give it, and we ask you to identify that invalid constraint, and we ask you that identify number of variables also. Sometimes we give it, you know, different scenarios. Like if you could look at the hand-woven carpets problem, you can just look at quickly, you can go back and check it. There are 70 plus variables are there. Is it right?
Yeah.
70 plus variables, because it's a dual LP problem. So we ask you that identify that number of variables in this problem. So such kind of question we ask you. Similarly, we ask you that identify the number of constants in this problem. We ask you that constraints like this, valid constraints we ask you, invalid constraint we ask you. But we never ask you that compute that optimized value, like drawing a graph, finding feasible area. We don't ask you. Generally, we give it a scenario and we ask you the finding of objectives, constraints, or variables and constants. This is one interesting question. Most frequently we ask in the week level. Okay. Yeah.
Sir, you told that the carpet we need 70 variables. So that is for 1 year. Like 12 months is 70 variables.
No, I don't remember actually.
So the time period also will be given.
Yes, yes. Maybe because it's a dual LP problem, each variable, it contains that set of values. Is it right? Hello.
Yes.
So due to that, each variable contains 12 values. So due to that, 70 plus variables you are getting. Of course, subscript variables only. WI, house, you know, what you call hiring, firing, everything is a subset. That is called dual LP. So that's one example, but we don't ask you such complex thing. We ask you simple question, but we ask you how many variables are there in this. Okay.
Okay, sir. We'll not be asked to do that.
No. We never ask you to solve that optimized value to calculate. In the linear programming model, we ask you only the constraints, objectives, count of variables. That's my one. That's nothing.
Not conversion from primal to dual.
Yes, yes. No, we don't ask you. You know, integer to fractional value, something like that. No, we don't ask you. No, we don't ask you that. Clear?
Okay, sir.
Yeah. Because week 11 is completely a theoretical concept where we don't have standard algorithm. That's the thing. We don't expect that. Simply real-time scenarios we ask you.
Sir, sir, how to calculate the number of variables? Could you please repeat that?
No, it is variables are very straightforward. No, here it is floor is
Three only.
Yeah, floor is having constant of that 200. 25 grams of fat is one constant. Clear? For the X type of cake. Similar to 100 grams of flour, 50 grams of fat are two constants, which is for Y. So here, two constants are there for X, two constants are there for Y. Clear? Hello.
Yes, sir. Yes, sir.
And there is a constraint constants are there. 5 case of constant is there. 1 case of constant is there. Here variables are only two, X and Y. Is it right? Hello.
Yes, sir.
So very simple. Whatever that X and Y value are changing dynamically, they are variables. Simple. They are not fixed. Based on the manufacturing limit and constraint, the values are changed. That's it. Here the variables are only two, but constants alone.
So, sir, do we have to say that here we have two variables and 6 constants?
No. If some other question, we'll ask you in that way.
Okay.
So we ask you that question is identify that the correct number of variables in this particular linear programming model.
Sir, I understand the variables. I'm not getting constants, like
Yes.
how to count. I understand that 200 is a constant, 25 is a constant. But if in the question it is asked how many constant and how to calculate them?
No, not calculate. 1,
No, right?
2, 3,
3,
4,
4.
5, and 6.
So we have to say 6 constants
Yes,
and 2
constant.
variables.
Yeah, it's just that's
Okay.
it. That's it. So that question understanding is the thing, and based on the question, see, simple problem only we'll give it. We don't give you the complex problem in the week 11 because it's a theoretical one. Whether you are able to understand the core idea of the problem or not, that's it. Clear? Mostly we ask you constraints, we'll ask you constants, we'll ask you variables. That's it. Nothing else. Okay. Yeah. Fine. Oh. Hello. Hello.
Yes.
Yes, sir.
Yeah.
Yes,
Yes.
sir.
Fine.
Yes, sir.
Yes, sir.
Cool. So this is about the linear programming model. Yeah, this is one interesting question. See, we have seen that, you know, graph with vertex cover, maximum independent, you know, minimum vertex cover. Linear programming model. This is what the linear programming model. What kind of question we get it is. And another mathematical models we do in the week 11 is network flows. See, if you go for the network flows, just quick recollecting what concept we have learned in the network flows is. Basically, the network flows is just you can just recollect it. Very simple. Every edge is having capacity of flow, CE, what do you call, you know, capacity of the edge. And flow allowed is FE, what do you call, you know, FE. Just you can check it. Ford-Fulkerson algorithm. Just quickly, oil tank flow. There is oil network flow is given. Always flow allowed is less than or equal to its capacity. Is it right?
Yes.
Quickly, just a simple kind of standard constraint or condition. Your flow allowed in the particular edges either less than or equal to capacity. Is it clear up to here? Okay.
Yes.
So using that constraint only, we are trying to calculate. So the next question, what they are asking is, consider there is a network is given, always source node is there, sink node is there, a target node. So given network source S and sink node T, with the numbers of the edges denoting the maximum capacity, CE, what do you call, you know, CE capacity across a particular edge, the value of the maximum flow allowed in this network is, what is the maximum flow allowed in this network is. So actually the calculation is very simple. We don't have any storage capacity for each edge, sorry, each vertex. Already we said whatever the incoming flow, we try to send as it is outgoing flow. Is it right? Is it right?
Yes.
A does not have any storage, B does not have any storage. Whatever 12 it is coming, whether 12 you are able to send it to the particular another vertex or not, we check it. So very simple. Whether outgoing, sorry, incoming flow is matching with outgoing flow or not, out degree. What do you call, you know, out degree. Incoming flow, is it able to distribute to the outgoing or not? Let's you take it. If you take 16, are you able to flow 16 from A to B and A to C?
No.
If 16 is coming, please look at this 16, 12 I can send it to A to B, 4 I can send it to A to C. Is it right?
Yes.
Okay, then no problem. That's okay. Whatever the 12 you received, you are able to send 12 directly from B to T. Is okay, no problem. But whatever the 10 you are getting, this 10, sorry, 4 you are getting, no, 4. This 4 you are getting. If this 4 is coming here, this 13 is coming here, 13 and 4, 17. Can we flow 17 from C to D?
No.
No. Can we flow, for example, 16 flow you allowed, 16 flow you allowed from S to A, then 12 will go to A to B, 4 will go to that A to C. Is it right?
Yes, sir.
Yeah.
After going to the C, if 13 is coming from S to C, this 4 and this 13, 17. Does 17 C to D is possible?
But sir, 4, sir, C to A is going 4, right? So it can divert, right?
Wait. Again, if it is going for C to A, means already A to B is saturated. Already it becomes 0. Already we used it, no?
Okay.
So
It
that's the
cannot
thing.
go.
Yeah. We need to identify that maximum flow allowed in this network means very simple. Whatever that each path is there, in that each path, we try to identify the minimum value. For example, in this particular flow, what is the minimum value allowed? Clear?
Yeah, it's here 12.
Exactly. So we try to identify the minimum values. First, let us S2 A, A2 B, B2 T. So what is the minimum flow allowed?
So 12.
Yes, 12 is minimum flow. Once 12 is allowed, this will become 0.
Yes.
Clear? Okay.
Yes, sir.
Yeah.
Here the remaining 4 is there. Here the remaining
8
is there.
8.
So this is over. This flow is over. Still any flow is allowed or not? Is it possible that another flow, S to C, C to D, D to T? How much flow is allowed? This flow?
So here it is 4.
This flow is 4.
So 4.
Because
Minimum value.
Yes. So S to C, C to D, D to T. So here the minimum flow allowed is 4. Not more than that. So it will become 0.
Zero.
Yes, saturated.
10
10.
It will become
9.
yes 9 because already 4 is consumed. So any other flows there?
Sir, S to A, then C,
S to A,
C, D,
then
B,
C, D,
B, T.
B,
T.
and T.
Yes.
Let me check it. So S to A, it's a 4. Okay. Then this 4 I can move it to C. Okay. This 4 I can move it to D. This 4 I can move it to B. This 4 I can move it here. So that this is another 4 minimum. Is it clear?
Yes, sir.
Yes, sir.
So in this way, if you go, this one will become 0. Then after it, so
6.
A to C will become 6. Then after it, C
10
to D,
minus 4,
C
6.
to D, it will become 6.
Then 1.
Then this 7 will become
1.
3. Is it right?
Oh, 4. Yes, 4 minus 10 minus
So
4.
it will become 4.
4.
This is 4 is over. Still any more allowed?
Yeah.
So what is that others?
S to C, then C to D, and D to B, and B to T.
So what is that minimum?
3. 3 is minimum allowed.
So S to C, C to D, D to B, and B to T. Is it right?
Yeah.
Yes.
So S to C, C to D, and D to B, and B to T. So that allowed is 3 minimum only because here is a 3. It will become 0. So 3 is a minimum. So this one will become 1. Clear? And this one will become 3. And this one will become 6. Over?
Yeah.
Okay. So any more allowed? Please
Yeah,
check it.
same path with 1.
Check it.
No, sir.
Yeah, same
No,
path.
sir, because anyway.
Oh, yeah.
This is
zero.
blocked. This is blocked. This is blocked.
Yes.
This is a blockage.
No path allowed.
So can you do the sum of these?
Yeah. 23.
Yes. So maximum allowed is 23. Maximum flow allowed in this network is with a different intervals. So that is 20. Not more than that is possible. But you can understand here, maximum flow allowed here, using it, we want to identify that what you call, minimum, what you call, minimum cut. Maximum flow if you identify, using it we can identify minimum cut. So I'll tell you, I think the next question is that minimum cut. First you identify the maximum flow. Once you identify the maximum flow, please look at the next question. So it is almost similar to this. I think they'll ask you the minimum cut. See, consider that given network, the source and this, with a number of edges denoting the maximum capacity across the edge. Which of the following edges is the minimum cut in the given network? See, already we got this graph as maximum flow allowed as 23. Maximum flow allowed is 23. To find out the minimum cut, we need to identify the maximum flow. Directly, we cannot find out the minimum cut. Minimum cut means the vital edges, if you cut them, entire flow can be stopped. What is the minimum cut? The vital edges. The vital edges. The vital edges. If you cut down that edges, you can stop this particular flow. You can stop this network. So here you can see that this 23 is there. No, this 23 is the maximum flow is there. If I stop at 23 flow, I can stop this complete flow. So how did you get this particular 23 is? I can cut that. A to B I can cut it. A to B I can cut it, which is a 12 value. A to B. And I can cut that. D to B I can cut it, which is 7. D to B. And one more cut I can do.
D to T.
This is 12. This is 7. And one more is
D to T.
Yeah. I can cut it. D to T.
Sir, can you just explain this again? Like how you are cutting it?
Yes. So if you find out the maximum flow allowed in the network, the minimum cut is, we try to cut down the edges, which are the vital edges, which the cutting of the edges sum is equal to maximum flow.
Oh, okay.
So here 12, 7 and 23 still remaining value is, this is 19 and this is 4. Is it right?
Yeah.
Yes.
So if you cut down this, we can stop the entire flow. Just you check it.
That's right, sir.
Exactly. But here, please understand, there is only one cut is available. There are multiple cuts are there. These 23 matched cuts are many cuts are there. You can check another cut is there. So if you could check it another cut, there is a cutting I can do.
14 and 9.
Another cut I can do is C to A. I can cut C to A. Is it right?
Yeah.
C to A is 4 value, no? This I can cut it. And one more cut I can do A to B. It's already there. A to B already we have thought about it. 12. This one. And one more cut I can do D to B because it's already there. This cut I'll do it. If this cut I'll do it, I can stop the flow.
No, sir. Like D to D.
Yes.
No, sir.
Yes. We cannot, because this S to C, C to D, D to T, I can run the flow. Because, this 23 it is matching. This 23 it's matching. But out of that, this is only that minimum cut. This is equal to 23, but it is what they'll give us. They will give multiple options which is matching to the maximum flow. You need to identify which of them is right. Really cutting that. So please look at here, valid minimum cut. Mostly what we check it, okay, 23 it is matching, 23 it is matching. So it is also minimum cut, it is also minimum cut. No. Please do that cut and verify that whether flow is stopped or not. So in this case, if you could see that there is, A to B, D to B, D to T, this is the right option. And they are trying one more option is C to A, D to B, C to A is 4, then D to B they are trying, is 7, and D to T they are trying, so that 7 and 4 and 4, no, it never happens. One more they are trying is A to B they are trying, this 12 they are cutting, C to D they are doing, C to D this is A to B is 12, it is 26. This is not true because by itself it is 26. This is not true. A to B they are trying, okay, A to B is 12. C to D they are trying 14, okay, this is 26. This is also not true. C to A they are trying, C to A is 4, this is 4, no? And D to B they are trying, it is 7. And D to T they are trying, it is 4. But here maximum flow allowed is 23. But here this is C to A is 4, D to B is 7, D to T is 4. So it is not, it's 11 and this is 15. This is also not true. But to make you confused, they will give this flow also. Because it is also getting 23, no? Clear?
Yeah.
But unfortunately, if you select this option, your choice is wrong. If you select this option, this is right. Because generally, what they'll think is that same 23 maximum flow, we found it. Whatever matched options are there, we are can choosing. No. Strictly you verify. Once you got the maximum flow, you try to identify that whether that maximum flow value is satisfying the minimum flow or not. And if you do a minimum cut, you cannot move any flow from source to destination. That you have to verify it. Clear? Clear? But here straightforward options. If they want to confuse you that another option, this option also they can put it. If this option you will put it, somebody might choose this one, somebody might choose this one. Whoever chosen this option, this is wrong. Whoever chosen this option is right. Because even I use it, this minimum cut is this, still the flow 4 is allowed. Still the 4 flow is allowed. Clear? Yeah.
Yeah.
But this has to be done by trial and error only, right?
Yes, yes, trial and error only. But we give it simple graph. See, some more previous year question, if you could look at, there is one more example I'm going. So there is one graph is given, something like this. See, here, there is one example. This is one more graph. I think earlier terms, maybe I don't know, I remember which term is. This is here, there is a T, there is a source. Let you take this as a source. This is a destination. What they try to give us, 3 and 4. Similar way here, they try to give it 4 and 3. So in this case, it is straightforward. Like, here the maximum allowed flow is 7. Is it right? Either you go in this way. So either you go in this way. If you go in this way, 3 and 4 maximum flow is this. Either 4 and 3 you are going is 7. In this case, what happens, you can do that a minimum cut you can do. What minimum cut I can do? Either I can do cutting of these two edges, like 3 and 4. This one I can cut and this one I can cut it. I can cut this and this. Clear?
Sir, what are the weights of internal edges?
No. Just only I'm telling. Let you consider it zeros. What is there? Maybe 1 and 1 or something. You consider some flow is there. But here we got maximum flow is, for example, 7. for example.
Yes.
In this case, the 2 minimum cuts are there. 2 are valid cuts, no? Is it right?
Yes.
2 valid cuts. Minimum cuts are here 2. Either I can cut down this edge and this edge, or this edge and this edge. In this case, what happens, here, in this case, we'll ask you that MSQ, multiple selection question. Because you have to select all valid cuts. In that way also we'll ask you. Instead of MCQ, we'll give you MSQ also. Clear?
Yes, sir.
So, because, to understand better, I've given you, because maybe multiple minimum cuts are there. All are satisfying that stopping the flow, which is the flow is not allowed. So this is another way, actually, they want to give it. Yeah.
Excuse me, sir.
Yes.
Can you show me the graph? I want to see the graph.
This graph. Okay. To find the minimum cut, you need to find the maximum flow first. Without maximum flow, we cannot do minimum cut. Clear? Okay.
Okay, sir.
So please look at here, 8th and 9th questions, both are linked. So first we need to find out the maximum flow. If they want to ask you that maximum flow, they directly give you maximum flow. So in the maximum flow, we need to find out each capacity. In that path, what is the maximum flow allowed? So this is all minimums. We'll ask it, we'll add it. So we get maximum flow allowed. Complete S to T. We are allowed with different intervals or different paths with 23. But this 23 can be stopped with edges cutting of these, like C to A to B, D to B. If you cut down it, this 23 can be stopped. But same 23 is matched with this and this. But don't fix that. 2 verifications you need to do. Either minimum cut sum is equal to maximum flow or not, and after minimum cut, either flow is allowed or not. Clear?
Yes.
Okay. Just give me 1 second. Yes. Yes. Here, so
Sir?
another, hello, yeah.
Sir, in the previous question, he found max flow by inspection. Like we did not use Ford-Fulkerson algorithm.
No. So
Example.
see, Ford-Fulkerson algorithm, we use it residual edges, reverse graph we are creating.
Yes, sir.
Every flow we try to do the reversing of the edges, and then we are trying to find out it. Is it right?
Yes, sir.
But that is, if it is a complex graph, the easiest way to find out the maximum flow is just directly we are finding the independent paths, like instead of going with reverse edges and all. So this is the easiest way. But I never tried it, residual graph building for this. Even in the theory session, we have taken a simple graph, something like, 4 edges, where the flows they are making. Is my screen visible?
Yes, sir.
So reverse edges they are creating, something like this. But I never tried that, Ford-Fulkerson algorithm on the complex graph. Maybe it works, I don't know. I never used it, which is the simple way, because finding the path, all minimums you're finding it and doing the sum pretty easy. Okay.
So in the exam, we'll give smaller graphs only.
Yeah, smaller graph only. We don't give it.
Inspection also we can.
No, we do. Complexity graph means mostly you are getting even in your like Dijkstra's and all these are only. Yeah, just give me 1 second. I'll join back. Yeah. Yeah. So can I go for the next? Hello.
Yes, sir.
Yeah. So quickly again, I'm going back. We have seen that week 11 linear programming. We have seen that network flows, and network flows in that you have seen that what exactly earlier problems you have seen. Independent set of maximum independent set, minimum vertex cover. It's a direct question, and maybe indirectly your finding means maybe graph will give it and we'll ask you that. That's another way. And the last concept of this week 11 is classification of problems. See, whenever they want to identify the classification of problems, first you should understand that reductions. Just quickly, I'm going for reductions. Even you can see that a bipartite matching problem is there. Like, even just to check it, the bipartite matching problem can be solved through network flows. What you call, there is a problem A and a problem B. Just it is a problem A, and inner we have a problem B. The problem A, to solve it, we take the help of problem B, so that the bipartite matching problem, it is reduced to network flow, but the input received from the problem A, it is converted into problem B input. The output received from the problem B, it is converted into the output of problem A. Is it right? There is a pre-processing step is there. There is a post-processing step is there. Hopefully you just to quickly recollect it. Is it right?
Yes, sir.
Yes, sir.
That we have done it theoretically. If problem A and a problem B is there, if problem B is helping to the problem A, if problem B is easy, problem A also easy. If problem B is tough, problem A also hard. We cannot solve it. That is what exactly they want to say about that reductions. But whenever they want to tell about reductions, they said about how these problems are solved as there is a classification of problems. Mostly all standard algorithms, which are sorting techniques, searching techniques, all these are having p-type problems, polynomial type, polynomial. Like, we try to find out that solution. Standard algorithm is provided for you, log n, n log n, sorting algorithm, merge sort. If it is searching algorithm of binary search, it is just log n. These things are polynomial. But some problems are there. They're hard problems, like hard problems, already knapsack problems, traveling salesman. So 0-1 knapsack itself is hard. 0-1 knapsack, whether you pick the element or not pick the item. One best example, where it is an exponential solution. Exponential. These problems are called hard problems. But hard problems are not forever hard. Some research is going on. Whatever the research is done, they preserve the work. So that in the future, the work can be enhanced by other researchers. Is it right?
Yeah.
Is it right?
Yes.
So that such kind of problems, what you call, some part of exponential problems are solved. Exponential problems are solved. Wait. I think something's wrong. Wait. Yeah. Yes. So some part of exponential problems is solved. Yes. Yes. Some part of exponential problems are solved. So even you could just check it that that week 11 open session. There is an algorithm. In that algorithm, step 1, step 2, step 3 is there. 2 and 3 are solved in p time. Solved in p time, polynomial time. But this particular step is not solved in p time. Not solved in p time. These kind of problems are called non-deterministic polynomial time. Non-deterministic polynomial. Is it clear up to here?
Yes, sir.
Non-deterministic polynomial algorithms. Now, dash is the class of decision problems that can be solved by non-deterministic polynomial time. Actually, this is, they are trying to just ask you that what exactly the NP. So some particular part of the algorithm is solved, some part of the algorithm is not solved in the polynomial time. So in future, they preserved for researchers, preserved. So such problems are called as NP problems. Polynomial problems are direct standard algorithms. Non-polynomial problems are hard problems are there, but some part of the problems are solved. Such problems are called as NP problems. So hope you understand. This is a direct question, which is NP. Clear?
So can you please repeat? I don't understand. The NP part.
Yeah, it is, for example, even you can check it, any linear search algorithm is there, no? Do you know the linear search algorithm? So we are having one index position. This index position, we are using a for loop iteration. Is it right? For loop iteration. So once this index is matched with that array of that index, is it matched with key value, we say that element is found. Element is found. Is it right?
Yeah.
This for loop is taking n complexity. Is it right? Because the iteration you are doing from first element to last element. For example, some researchers is work, they identified directly get the index position with unit of time. Unit of time means 1. Is it right? Hello?
Yes, sir.
Yeah.
If that case is done means this entire linear search complexity it is reached to O of 1. Is it right?
Yeah.
Yes.
Similar lines, some problems are there. For example, your knapsack problem is there. 0, 1 knapsack. Just quickly you can recollect it. 0, 1 knapsack. There is a list of items are there like 2, 4, 3. There is value of items. First item value is 2, second item value is 4, third item value is 3. Your bag size is 5. Your bag size is what? 5. Is it clear? Hello?
Yes, sir.
Now you have to fill this bag with a different combination of items. Either first item and third item you want to fill it, first item and second item you want to fill it, or only second item you want to fill it. That combinations you need to try it. Is it right?
Yes.
Also, Yeah, all combinations. So how many combinations you need to try is 2 cube you need to try it. Is it right?
Yes.
Yes, sir.
So this is exponential solution. Is it right?
Yeah.
Hello? Hello? Somebody
Yes, sir.
asked about. So now this problem is a hard problem. Is it right?
Yes.
Some researchers are working on it, how to reduce the complexity of this particular knapsack problem. They figured out some steps. They are not able to figure out some steps, so that they figured out step number 2 and step number 3 in polynomial time. But step number 1, they are not able to figure out it. Such problems, what happens, they will move from hard to NP category. Is it clear?
Yeah.
Is it clear? Hello?
Yes, sir.
Yes, sir.
So that is a
Means
basic fundament. Yeah.
Which are
Moving
partially convertible to polynomial, right?
Exactly. Some researchers are figured out some steps so that they partially move from NP hard to NP problems. Up to it's clear, no? Theoretical concept.
Yes.
So
But
NPR means all the components are in
all
non-polynomial.
components are exponential.
Okay.
All steps are exponential.
So we don't know anything.
Yes, we don't know anything, and we don't know some particular research are working or not also, we don't know, because still now no research is preserved. Clear?
Yeah.
Yes. So this is straightforward. Actually, this is only expanded format of non-deterministic algorithm. So the right answer is this. But here, please look at here. Yeah, this is satisfiability. What you call. Instead of going for that, I don't want to. But the 12th one. Sorry. Yeah. 12th question I get back because it is satisfiability, which is conjunction normal, that is okay, different. I'll get back to this one. Let's we complete this 13th one first. So here an algorithm A is NP complete if it satisfies two conditions. See, I'm just drawing that famous circle. This is a famous circle and famous diagram to differentiate between that NP hard and NP. This is NP hard. Basically a problem. It does not have any research work is done. The problem is basically in the NP hard category only. So NP problems are the NP problems where some part of the problems are figured out. Is it right?
Yes.
Is it right? Fine. So this is okay. Now an algorithm A is NP complete if it satisfies two conditions. So here, this is the intersection area. This area called NP complete. Why we call NP complete, I'll tell you what exactly this one is. So A is in NP because it is the non-deterministic polynomial time, because some part of the problem is solved. Every algorithm in NP is a polynomial time reducible to A. So what exactly, this problem is the NP complete. Sorry, NP. Later, what happens, this particular A, this P is there, P is extending its scope. Like, maybe all part of A also solved in P time. Is it right? Is it right? Because some parts are already figured out in P solution. Some part of the solutions are not done. So until that it is an NP category, later it is problem is completely occupied with polynomial time. Is it right?
Yeah.
So here, the NP hard problems, if they are figured out solution, they will immediately jump it into NP, which is called NP. Similar way, NP, some particular part is solved in that. So there is an intersection area. What this intersection area is called as NP complete. So this is periodically changing. Some problems are moving from NP hard to NP. So NP problems are extending its scope to polynomial time. Like, the polynomial size is increasing whenever research is going on. This particular intersection area is there, the commonality between NP hard and NP complete. So NP hard and NP. So this commonality we cannot say that either 5 or 6 problems. It is a dynamically changing one. Dynamically changing one. And periodically, which is every fortnight, we don't know, research is going on with a rapid speed. So what do you call, the rapid length of it. Today, whatever the today research is there, tomorrow it is extended, something like that. That is what happening. Here, do you say that either both statements are true, one of them is true? Both yeah, both statements is true. Is it right? They clearly said
Sir,
algorithm
second statement, can you explain?
Yes, every algorithm in NP, this one, there are a lot of algorithms are there. NP is polynomial time reducible to A. So because A is currently partially worked out solution, later what happens also, A also taking the help of other algorithms, and A also completely reducible to polynomial time. Clear?
So here the intersection is A.
Yeah, maybe intersection A, it goes to intersection area. Maybe A, it is located here, means it might be intersection area of NP hard and NP. Maybe A is located here. No issue. Because A is having a combined features of NP hard and polynomial time. No? Clear? It's intersection area. What do you call it? So A is in NP, that's a true. Every algorithm in NP. See, along with A, some algorithms also there, no? Clear?
Yeah.
See, one more thing I want to tell you. If one problem is solved, because I'm talking about reductions also, because already I said about reductions. Maybe some other problem is solved. Due to that problem is solved, A also can be solved. Is it right?
Yes.
Is it right? So due to that, that's what every algorithm in NP is a polynomial time reducible to A. So might help to the A to become A as a polynomial time. Is it right?
Okay.
So that's what I said about reductions. Oh, sorry, my reductions are gone. See, reductions already I said about it. Problem A is there. It is a harder problem. It is taking the help of problem B, where it is a easier problem. When the problem A is solved through B, so there is a pre-processing step is used, there is a post-processing step is used. If B is easy, if A is reducible to the B, then A also easy. Is it right?
Yes.
Is it right? If B is hard, A also hard, because you are trying to reduce A with B. When B is hard, you are trying to reduce A to B. A also hard. We cannot solve it. That's the same thing. What they are studying about, that is reducing. We already A is there in NP location, but some more problems are there in NP. They are already having in polynomial time. They can reduce A. Yes, they can reduce. What is that? Because
sir, it says every algorithm in NP is polynomial time reducible to A, means those problems in NP can be reduced to A.
Yes, see, very simple. I will tell you. Sorting is there and setting is there. Is it right?
Yes.
So sorting and setting is there, no? See,
Yes,
if you want to do that log and setting, the input must be sorted.
Yes.
This is a pre-processing step. Is it right?
Yeah.
So that's why some particular algorithms are there. Every algorithm in NP, whatever other algorithm, maybe A, B, C, these things are there. They already got the solution in polynomial type, for example. They might help to A, no? Here.
Yeah.
They might help to A. Yes, you can. They might help. So because
Sir,
of
but it
B and
says
C,
reducible to A means those problems can be done with the help of A.
no, here reducible means it might be a, somebody is helping to A. I think so. That is, plus you check it, a dictionary kind of mean. Polynomial time reducible to A means they are trying to reduce the complexity of A. Clear?
Okay, got it.
They are trying to reduce the complexity of A. See, one more thing. 0-1 knapsack problem, they are trying to reduce the complexity, means they don't work 0-1 knapsack problem. They try to work out a common kind of theory. That theoretical solution will help to lot of algorithms. Clear?
Yeah.
Clear? That is simple. So
Sir,
here both. Yeah, tell me. Yes.
so NP will include both, like the problems that can be solved in the polynomial time and that cannot be solved.
This is NP. Here some problems are there already. They have got solutions in polynomial time. Clear?
Yes,
Clear?
sir.
Because this scope is extended. Like today 2 problems are there. Tomorrow 3 problems will come into the scope. Clear?
Yes, sir.
Now A is located here. Someday A also will join into polynomial time. Fine?
Yeah.
Clear? That is what they want to tell you. Simple. Clear?
Yes, ma'am.
Because some other problems, they are trying to reducible to A. They are trying to help to A. So that maybe it's possible. They are trying to help you to the A. To bring the A into polynomial time. Initially A is in NP. Later A also come into the category of P time with the help of other problems. Okay?
Yes, sir. And so if
Interesting.
in the second statement, like NP hard was written, not NP.
Yes. NP hard is not there. For example, NP hard is here. Clear?
Yeah, and A is there.
No. Let me consider. For example, A is here. Clear? So now this A definitely it will not be here.
Yes, sir.
Clear? So, but some researchers are there. They worked some steps. Clear? Some
Yes,
steps
sir.
they figured out in polynomial time. Then what happened, this A will come into this intersection area. Maybe in this area means maybe it is intersection area. Maybe the size of hardness is decreasing. So whenever intersection is like this, maybe your hard is joining most of the part here. Clear? Hello?
Yes.
Hard problems may be joined into NP. Is it happens? No. It happens.
Yeah.
So this intersection area is increasing. The intersection area increasing means more problems from hardness to they are coming into the NP category. After coming into the NP category, they might enter into the polynomial category. It happens, no? Simple. This kind of intersection is called as NP complete.
So then also like the both statements like will be correct for NP complete. Whether A is present in the
NP complete statement is not given, no? They haven't given. If they will give it statement, that is also correct. Intersection area they'll talk about NP complete also. Okay.
Yes, sir.
Now this 12th one
I have one thing to ask. See, like you gave one example earlier, like there is a problem, there are 3 steps. Now when there is no solution in any of the steps, it is NP hard.
Yes.
And when there is a solution for maybe partial 1 or 2 steps,
yes,
and this goes to NP, right?
Yes.
And where does this NP complete stands here? I mean, with this in these examples.
See, they reserved one particular preserving work, See, it is a dynamical change. We cannot say this NP hard. We cannot quantify, Here today it's 5 problems are there. They are in NP hard category. Out of that, 2 problems may be coming into this category. Maybe 1 problem. Is it right?
No, what I'm trying to tell is, say there is one. Let us take one problem only. Okay, there is one problem, which was say in NP hard category. Okay, all the 3 steps were not able to be solved. Okay, now with research, 2 steps or maybe 1 step we could solve in within this polynomial time. Okay,
yes.
So that with that this NP hard this problem will move to NP, this left circle, right?
Yes.
Now there is intersection in between.
This part.
So okay, so in which condition the
Hmm.
problem will come here? I want to know that.
See here, there is a dynamic change. The dynamic change we cannot quantify. Like, NP hard problem, it come into the category of NP complete. But see, I want to tell you about research. First, basically, researchers, whether you find something, is it clear? Is it clear? A new invention. Am I right? But somebody else came with, your invention is wrong. Somebody might prove it, no? So what happens that this NP problem, again, it will come into the category of NP hard.
Correct.
So that's the thing. This NP complete is a dynamic one. We cannot say this particular NP hard is directly enter into it. Sometimes what happens, this NP again getting back into that NP hard also. Is it happens? It happens, no? Hello?
No, but I see what I'm not able to understand is what is the difference actually in between this.
See,
NP NP hard I'm clear, but this NP complete I'm not able to
that's what the
understand
thing.
exactly.
This NP complete, combined features of NP hard and NP, is it right? Is it right?
Well, it can be either of this.
No, either of this, whatever you said, either of this. So you proved it. This solution is correct. Somebody else came that your invention is wrong. See, research means what exactly, you say that this particular part, you said it is okay. This is possible. Somebody came it, they say that this is not possible. In this particular edge case, your research is not possible. That is also research. Is it right? Proving something wrong in the somebody's paper also research. Is it clear?
Yeah.
So that's the thing. There is a chance that already identified NP problem, it might enter into that NP hard also. Is it clear?
Okay, so those type of problems will come into NP complete.
Yes, NP complete is a two dynamic one. Either of this. Clear?
Okay.
Hello? So there are a lot of references say that you are correct. There are a lot of research references says that they are incorrect. Final proving, someday it is going to be solved. Understand? Research means always we are not proving. Somebody else wrong also saying it is a research. Is it right? That is what called as NP complete. So they don't want to disconnect these two particular circles. They want to intersect always. That's what the thing is. See, actually, advanced LV is one elective subject. Whatever we entered that week 11, that is the starting week of advanced LV. Basically, they start with this particular concept only. Basically, okay. Okay.
So
yeah.
So NP hard, there are the problems which are hard and have not been done any research comes under NP hard.
Exactly.
And if there is some research done, some of the problem is solved, half of the problem or some part of the problem is solved to polynomial, then it will come to NP.
Yes.
And NP complete is that middle ground where they are in dilemma whether to keep it in NP or
there is a
NP
dynamic
hard.
move. There is a dynamic move is happened. Yeah. There is a dynamic move is happened because of a continuous research. Some problems are moved from NP to NP hard. Some problems are moved from NP hard to NP. Clear?
And if there is a doubt, then we keep it in NP complete.
Yes, because maybe somebody else is being proved that you're wrong, you're right, something like that. Okay.
Yeah, got it.
So if in out of 3 steps, if we say we make step 1 as polynomial time and there is nobody to oppose it, then we can say
polynomial time is very clear. Standard algorithm, no?
No, sir. There are 3 steps and 2 are NP, and 1 step we make it P.
No. There is no such thing like 1 step only non-polynomial time. So 2 steps are polynomial time. So polynomial time is dominating that NP. No, they want to preserve that research work. For that, they say that till now we got the solution is NP. They don't say that this is P and these two are NP, so that we don't say that. 2 steps are NP, 1 step only is solved. It. No such thing. You only preserve. So if you a problem came from NP hard to NP means you are intimating to somebody some part of the solution we solved it. Please proceed with the solution. Clear?
Yes, sir. So for some part, if there is no opposition, like nobody
No.
is saying disapproving us, then it is NP.
No,
For
no.
that also some test cases are passing, some are failing.
Yes,
Then
somebody.
it is NP come.
But they don't say that major steps are polynomial, minor steps are NP, major steps are NP, and minor steps are there is no kind of quantified value. Only we preserve it. We preserve it as a research work. We preserve it. Later, somebody study on it. Again, they will prove it whether you are correct or wrong. That's it. Okay.
Yes.
Yeah. The next one is satisfiability. If you could see that whenever CNF conjunction normal form, if you could see that satisfiability problems, if you could conjunctive, see this one, yeah. So conjunctive normal form, we are using Boolean formulas. Actually, you can see the Boolean formulas. So the Boolean formulas, we are applying that literals, where just I'm recapping the literals with some operators we are using, like AND operator we are using, OR operator we are using, and negation operator we are using. Possibly you can check it. What do you know? 2 SAT satisfiability problems, 3 SAT 3 satisfiability problems. You can quickly check it. Whenever a class is given, the class it contains the different literals are there. We try to combine the classes with Boolean values, true and false and true and false. So here you can check it. Which of the following class does that CNS satisfiability problem satisfiability? Conjunctive normal, conjunctive. So conjunctive normal form. So please look at here the conjunctive normal form problems. If you see that there are 3 variables they are giving, like x value, y value, and z value. Initially they specify the true, false, and true, something like this, maybe some Boolean value. Please check it, whatever it is. Which class of the problems does CNS satisfy problem belongs to? What exactly, are you sure that is it NP hard problem? Are you sure that is it NP problem? Are you sure that is it NP complete problem? That's what the question. Which class it belongs to? Definitely it is not polynomial type. So these literals values are always it is Boolean values. Possibly you can check it. Maybe classes are there. The class it contains that x value and y value and z value is there, something like this. Similar way, x value or y value or z value is there. Between these 2 classes, you might have AND operator. Is it right? If you could see that the classes and literals. Is it right?
Yeah.
So these kind of problems, which class it belongs to? Whether it is NP hard, NP, or NP complete. Here the literals are, Boolean values. True, false, false, true, something you are getting.
So CNF satisfiability means like 2 set or 3 set problem.
No, either 2 literals you are using, 3 classes you are using, 4 classes you are using. That's what 4 SAT, N SAT, 2 SAT. Only 2 literals are there means 2 SAT. 3 literals are there means 3 SAT. That's simple. Now, forget about SAT, because to understand what is the background work I want to tell you. But here CNF satisfiability problems, what kind of problems, what kind of classification of problems, whether they are NP class, P class, NP complete, or NP hard? How we can say? What kind of problems category? Is it polynomial time?
No, sir.
No.
Definitely
No,
no.
definitely not
Exponential.
polynomial.
Definitely no. Yes. Then what else is there?
Sir, NP complete, I guess.
How do you
NP.
say that it's NP complete?
Sorry, sir.
How do you say that it is NP complete?
Sir, maybe because
See, NP complete is a dynamic kind of problems which are moving from that NP and NP hard between. Is it right?
yes, yes,
So based on this particular literals like X and Y and Z, the particular, conjunctions we are changing. Either we are using, conjunction value or disjunction value, either or and and. Is it right?
Yeah.
So we cannot say completely this is NP kind of problem or NP hard kind of problem. They are in between that NP hard and NP. So either or, either it might belongs to NP class or either it belongs to NP hard. So the right answer is this. So we cannot say completely this is NP class, this is completely NP hard. So the right answer is that NP complete.
So could you repeat this part, sir?
Yeah, because we are using conjunctions and disjunctions. See, conjunction operators, disjunction operator, and an or is there. Is it right? Hello?
Yes, sir.
So that using conjunction and disjunction operators, one problem, it might jump from like, either NP class non-polynomial category to hard category or hard category to NP category. So we cannot say it is NP category. We cannot say hard category. So that's the thing. All CNF problems are satisfiability problems are going to be NP complete problems only. Because see, this X and Y and Z values are Boolean values, no? These Boolean values, we don't have any kind of, a constant kind of computation like a unit of time calculation. Sometimes we get true value as input, false value as input, true value as input. These things, 2 SAT, 3 SAT, 10 SAT problems, we cannot say completely this category. So they are in dynamic kind of change. Based on 3 literals, 4 literals, their classification is changed.
So if you use X and Y and Z, then it is polynomial time solvable.
Wait. X and Y and Z you said is right. What is my class? What is my class? You are trying X or Z, sorry, Y, I'm sorry, X or Y or Z. Then either you can take X value true, Y value false, Z value false, then no problem. This entire one is true only. Is it right?
Yes, sir.
But this X and Y and Z, we don't know that. Is it right? The input values, we don't know that, no, the variables literals values. Is it right?
Yes, sir.
So CNF satisfiability, all it belongs to that Boolean literals only we are using. Whenever Boolean literals we are using, the values which are getting true and false, we have to change it based on disjunctions and conjunctions. We cannot say it is completely NP hard and NP. They are in, dynamically they are changing based on Boolean values and based on clauses, what clauses we are using, based on whatever operators we are using, what you call, and or not. All these 3 things will decide. Clear?
Yes, sir.
That's the thing. Reductions we are applying. 3 SAT problems we are reducing to 2 SAT. N SAT problem we are reducing to 3 SAT. Something we do it like that. Okay.
Yes, for some input combination we can solve it in P time and for
Exactly.
NP.
Yes. So that they are in dynamic change. They are in dynamic change. We cannot say, polynomial time. They cannot say definitely not polynomial time, and they are not belongs to NP, they are not belongs to NP hard. That's what it is. Yeah.
So since we don't have these Boolean values or clauses or operations, so we are keeping it in NP complete because it is dynamically changing.
Yes,
But
yes.
is it possible that in the exam there will be these Boolean values, clauses, and
No, no, no.
operations
We don't
given?
see, this is a theoretical concept.
Okay, okay, okay.
All this is theoretical concept. We give you diagram and we ask you the theoretical question only. We don't ask you the clauses which is defined in the live session or video lecture. That questions we don't ask. Only theoretically we get it a question something like this.
Okay.
Yeah.
So you mean the problems will not be asked?
No. We don't ask you the problems. We don't
Only this
ask
theory.
only theoretical concept. Regarding classification of problems, we will ask you theoretically between the NP hard, NP, and NP complete. And regarding the linear programming, we ask you that a real-time scenario with literals, variables, objectives, and constraint. And regarding the network flow, we ask maximum flow and minimum, cut. All these are. That's it about that week 11. That's it most. That's it. We don't ask you problems. Definitely, we don't ask. Like finding optimized value like sweet shop. We don't ask you 3-SAT diagram, 2-SAT diagram. Even just I talked about reductions. No problem.
Yes, sir.
Reduce. No, we don't ask you such questions. We don't ask you such questions.
Okay, got it.
Yeah. Theoretically, we'll ask you. Yeah, this is mostly done.
Sir.
Yeah, tell me.
So there is also one concept called checkability. Like in polynomial time, we can check or solve in NP. So,
yeah. That is verifying problem. See, verifying problem. See, just a minute. I'll just open verifying. See, this is interesting example. Even Professor Madhavan is given very good example. Just a minute. But I'll go with a different example. No issue. Yes. See, look at here. Your problem, your solution is hard solution. What do you call NP hard? It is exponential time what it is taking. So I'll go with the example. For example, you have given to a problem to the student that is find the sum of subset equal to 10. So the subset he wants to find out that is equal to 10. We have given a list of values to the student. The list of values I've given is 2, 3, 7, 6, 4. So this list of values I've given to the student. I want to ask him that please find a subset. So that subset sum should be equal to 10. The student, he has done some solution. We don't know what his solution is. But the exponential solution, he did it. He came with, sir, I got the subset. The subset is this, 6 and 4. Or he has coming with some other subset. So maybe he's coming with another subset is called 3 and 7. The 3 and 7 sum is 10, no? Is it right?
Yes, sir.
6 and 4 sum also 10. Is it right?
Yeah.
He worked out solution. Maybe he tried with 2 with other combinations, 3 with other combinations, 7 with other combinations, 6 with other combinations, all combinations he's tried. But he got this list. Sir, this is the list which is matching to 10. So now this particular algorithm, this algorithm is, sorry, this algorithm. So maybe, my particular, this 10 subset we are getting, the student has been worked out a solution, something like 7, 6, 4 is there. It came with the output. It came with the output result. this list he came, like, he found that particular, this is possible and this is possible. Now we are using some verifying algorithm. This is called verification algorithm. Verification algorithm. This is actual algorithm. This actual algorithm is hard. This algorithm is what? Hard. Is it right?
Yes, sir.
Yeah.
This verification algorithm is a polynomial time. Why it is polynomial time is to get this 10, whether this particular output is correct or not, just I need to do n iterations on list 3 and 7. Is it right? Because just I have to do the first element to last element sum. Is it equal to 10 or not? I need to verify. So it is a p time. It's a p time. No, you're doing.
Yes, sir. Often.
Yeah.
So that checking algorithms is polynomial time. Checking algorithm is polynomial time. This is another example. Even in the professor lecture, he said, I think he said about sum of two numbers we are giving to a student, and student is coming with a result. Whether the product value is matching to our result or not, we are checking with the polynomial time. That kind of algorithms are called as checking algorithms. Maybe harder problems are there, but their checking algorithms are polynomial time is there. Whether that solution is correct or not, we will verify in the polynomial time. Such such problems are called as checking algorithms are polynomial.
So NPR problem can have the checking algorithm can be in P.
Yes. Maybe NP problems are having checking algorithms are polynomial time. Already checking facility is there. Whether the solution is correct or not, we'll verify. But we don't verify that solution they did it. Whether in polynomial time, we don't verify. Clear? Yeah.
Yes, sir.
Cool. Yeah. Anything else?
And sir, question based on Ford-Fulkerson algorithm can also be there, right?
Maybe if we'll give it, there is simple graph we'll give it. We don't give you the complex graph and we'll ask. So actually residual graph, see, 4 edges, 4 vertices, Ford-Fulkerson algorithm. See, in that case, what we'll ask is, we'll ask you that clever and bad flow. We don't ask you that compute the maximum flow. We'll ask you the clever and bad flow. For example, something like this. This flow is there. This flow is there. They'll say that this flow. They will say that this flow. They will show that this flow. They will say that this flow. Out of this A, B, C, D, which of the below is the bad flow? We'll ask it that way.
Okay.
We don't ask you that flow, which is the clever flow, which is the bad flow in the list of options. Okay.
Yeah, got it.
Bad flow means which is lesser than this maximum flow, correct?
Hello. Yeah, tell me.
Bad flow means it is the flows which are lesser than the maximum flow.
Yes. Yes. One of the path is wasted. Like, instead of using it, it is unused path. Due to that, the maximum flow is not allowed. Okay. That's
yes, sir, it blocks other paths.
Yes.
Because of this.
Yeah, one edge is unutilized, underutilized. Yes. Okay. Yeah.
And clever flow?
Clever is we are trying to use it, all paths which is saturated point up to saturated point. Even just you check the graph, some flow is given 1 and 1 all ones is given. I think so. Maybe I think just one graph is there. Yeah, it is this. I think this way it's there. Is it right? I think so. I don't remember actually. This way, and this way is there. Is it right? Maybe I think so. I'm sure. 1. I think yeah. This is 1. This is 1. This is 1. See, actually, the clever flow is you can go in this way. You can go in this way. Maximum flow is 2. Is it right?
Correct.
Yes.
For example, by mistake, what it did is the bad flow is 1 flow they are utilized in this way. Due to that, what happens, you cannot use this flow. You cannot use this flow. So here the maximum flow, it reaches to only 1. Actually, because of the bad flow, it is reached to 1 only. 1 is missed. Is it right?
Yeah.
Yeah.
So that kind of question we'll ask you if we want to ask the Ford Wilkerson, like identify the bad flow, identify the clever flow, like list of options we'll give it, and we'll ask you. Mostly we'll ask you in that flow if it is Ford Wilkerson.
Got it.
Yeah.
Now, in the left case, what is the clever flow?
The clever flow is this, no? This is first flow, and this is second flow. So
the max flow.
Maximum is 2. Maximum is 2. Yes. We are utilizing this flow, no problem. Maximum
So
is
maximum flow is the clever flow, right?
Yes, maximum flow is the clever flow. If less than the maximum flow you did it, means that is a bad flow.
It's a bad flow, yeah.
Yes.
So if you have to find the maximum flow, then we can do by inspection or Ford Wilkerson, right?
Either Ford Wilkerson, simple graph they'll give it is Ford Wilkerson, or inspection only better, because simple graph you can do it by inspection only. If inflow is equal to the outflow, like flow capacity, in degree, out degree, both are same, so we allow it. That's it. Okay. Yeah. I think it's okay. So again, I think
yes.
mock will be released on tomorrow. On the mock, we are getting, on Friday we'll have a discussion. I think, yeah, tomorrow I think they'll release it, not issue. Similar kind of questions, maybe, at mostly second week to 11th week, all of them are equal weightage. Mostly, complexities, these questions mostly we are getting. And regarding graphs, we are getting most of the questions, which is, commonly. Stacks and linked list also we get it 1 or 2 questions, which are combined concept of it. And DFS, BFS also, where what kind of data structure behind you are using. DFS we are using stacks, BFS you are using queues. That yeah, it is okay. But anyway, we have a mock session. No? We'll understand better. So I think
okay, sir.
We can stop the session.
Sir, I want to.
Yeah, tell me.
So what is the total bonus one? PDSA.
Bonus is on OPE is there, no? On the OPE, if you sort that all of them, you get the bonus, 3 marks bonus. If live problems are there, no? I think live problems are there, weekly live problems up to 9th week it's there.
Yes,
yes.
11th week is not there. 11th week, no problems, because practical stand algorithms are not there. Up to the 9th week, if you did that, I think 4 problems or 3 problems are there based on the week complexity, So
yes.
That 3 marks you get it bonus. And OPP examination, if you got the marks, that weightage is added to enter, but OPP is not eligibility for enter. Either you attempted OPP or not, you are eligible for enter. That bonus you get it. Live coding problems bonus you get it.
So mock also 2 marks, right?
Mock are you getting bonus? I don't know. Is it right?
Sir,
I don't know.
What is the breakup, sir? If the bonus, because right now I got 2, but I thought the total was 5, so I'm wondering.
I don't know about bonus.
Yes, sir. I also got 2. I was also wondering, like it was 3 for live coding, right?
3 only.
But I got 2 only. I'm not sure why.
Just can you ask Atulji? Maybe he knows well, like right calculation.
Okay.
Yes, sir.
Yeah.
Okay.
Thanks a lot, sir.
Yeah, thank you. Bye. Have a great day. Bye.
Thank you, sir.
Okay.
Thank you,
Good
sir.
night,
Good
sir.
night.
Thank you, sir.